Zapraszam. So we should start. Welcome everyone. So this is a special occasion, which is due to the medal of the Czech Academy of Sciences. So among our participants, we have Professor Vladimir Karas, researcher of the Institute of Astronomy of the Czech Academy of Sciences. And he's not our usual participant because he came here with a special mission. He came here as a representative of the whole entire Czech Academy of Sciences to give medal. So Vladimir, the floor is yours.
Thank you very much. Thank you very much. It's a great pleasure to be here. I would like, first of all, to thank the organizers for the opportunity this early morning, and also to congratulate to your institute for interesting conference and for the anniversary. But as Krzysztof already mentioned, this opportunity here is directed to two particular people or connected to two particular people, one of whom is the member of your institute, Professor Czerny, and the other one is Ernst Mach. So I just say a few words about the connection and why we do actually this ceremony. The Czech Academy of Sciences has this medal which the president of Academy awards to eminent physicists or astrophysicists for their lifelong achievements and for work in physics, of course in some connection with the Czech Academy of Sciences. And so there is a very good reason also to award this medal to Božena Černý, because with our astronomical institute, which is part of the Academy of Sciences of the Czech Republic, we have a really very long and I should say fruitful collaboration. So it was 2 years, more than 2 years ago, that our institute proposed to the president, Professor Zajímalová of the Czech Academy of Sciences, to give this medal to Božena, which she decided in late 2019, and then things stopped. Usual procedure used to be to do the ceremony in Prague, actually, to invite awardees and to give them in once a year this medal, but that was stopped, and now we realize that there is this very nice chance actually to use your conference and your celebrations to bring the medal here, because there is a very unsure outlook for the autumn, and maybe we would have this medal for a long time in the drawer, or the president of Academy would have it. So now about the Ernst Mach, I think I do not need to say much, because he is certainly known to everyone in the room. Just the connection with Czechia or Czech Republic. You probably know that he was born near Brno, second largest town in Moravia, very beautiful university town, and then as is written on this plaque, he became a rector of the university in Prague, of technical university, and professor of experimental physics for quite a number of years. So this is wall of the Charles University in Prague, where this face, bust, and the text was put in 2016, when there was anniversary of the death of Ernst Mach, and where we also do these ceremonies normally in central Prague. And I just note that for astronomy, he has, of course, particular relevance. First of all, the idea, which is not exactly part of general relativity, but stands behind him, is the Ernst principle, obviously. And Albert Einstein, who was in Prague 1910-1911 working on his ideas before the general relativity was formed, acknowledged Ernst's ideas already at that time. And in his general relativity scalar theory, not yet final theory, he already had incorporated these effects in the sense that inertia of a body is related to the movement of distant matter. At that time it was linear movement, but as you know, similar effects we have in general relativity, and astronomers who very much work on the subjects of rotating black holes know the frame dragging as a certain aspect of Mach principle, perhaps. But another point is about shock waves, motion with speed exceeding the speed of sound, which is also attributed to Ernst Mach. Not so directly related to Božena, who works very much on spectra and line profiles and emission lines. Ernst Mach actually did not believe in the existence of atoms in time when many people did accepted the notion already, but that is just a side remark. So let me conclude this brief introduction and congratulate to Božena. Maybe Božena, if you can come here. No, I don't have enough hands, but I would like, first of all, to congratulate you and to give you the medal, which is inside, I hope. And that is personalized with the name on the back. And there is, in addition, this diploma connected with the medal, which says that President of the Czech Academy of Sciences awards to Professor Božena Černý the Ernst Mach Honorary Medal for merit in the physical sciences. Prague, October 29, 2019. Professor Eva Zažímalová.
Thank you very much. Maybe I will use the microphone. Thank you very much, Vladimir. It's extremely nice summary of our long collaboration. I don't know, certainly more than 20 years, and I don't know how many papers, counting everything, it could be 50, I guess. Anyway, it's a great pleasure for me to receive this award, and well, my reflection is that everything is just always quite complicated. So the ceremony is delayed by 2 years. Our workshop is delayed by 1 year. then, of course, I work with spectroscopy, while Ernst Mach didn't believe in atom existence. On the other hand, my initial motivation to study physics was really in childish interest in time and space. So when I was at school, I read Mr. Tompkins in Wonderland, and then I started to think, but what really is time and space? And then I entered physics department, naively believing then I will get the answer. Well, then slowly I didn't quite get it, and then I realized that general relativity is not the final answer. Nothing is final answer. And general relativity was already invented, so I wanted to do something new, and then I started to do astrophysics, and I was doing astrophysics all my life, but this time and space was an inspiration for me. Thank you.
So thank you very much. You should know that Professor Bożena Czerny was also very successful, not only before, but especially recently, because during last year, we received in Poland the first ERC Synergy Grant. I mean, the first one in which the main institutes comes from Poland. This is the Nikolaus Astronomical Institute, so-called SAMK. And Bożena Czerny is PI of this project, in one leg of this project. And because of that, we decided to produce a movie about her research, about Bożena. So now please enjoy.
Constant was measured in different places. This is this Hubble constant, which describes expansion rate of the universe, and its measurement from supernovae and independent measurement from a cosmic microwave background gave different results. The difference is only by 10%, so you may think it's not a big problem. However, the claimed accuracy of measurements is small as 1%. Either we need a new theory of gravity instead of Einstein general relativity, or we need vacuum energy, and then this vacuum energy should depend on time.
Scientists from the Center for Theoretical Physics are developing an entirely new way to determine the rate of the cosmic expansion. It is based on quasars, the most distant objects in the known universe. That could provide important new data to solve the Hubble constant discrepancy.
Because those claimed measurements seem to be accurate, but there is always a danger of systematic errors, then introducing new objects is important, and we can use quasars as those new objects to measure the expansion rate of the universe. Quasars were discovered over 50 years ago. It is just an active nucleus of a galaxy. In the nucleus of a galaxy resides a supermassive black hole, and the mass is of order of million or even few billions of solar masses. The advantage of having quasars is that we can observe them relatively nearby as well, but up to very large cosmological distances. On the other hand, using them to determine the distance is not simple, because we need a special method to do that. And here comes observational aspect of quasars. Those are strong emission lines seen in their spectra. 10 years ago, we proposed explanation how those lines form. Everybody knew that we have the central supermassive black hole, an accretion disk around this black hole, but then we realized that from the surface of this accretion disk we can have very, very strong winds if the temperature in the disk is low enough, like 1500 kelvins, and then the dust can form in the disk atmosphere. And this material irradiated leads to formation of lines. So we still need a distance from the black hole to this broadline region, and that can be determined from quasar variability. Fortunately, all quasars are strongly variable. Radiation which is liberated close to the black hole varies, and this variable irradiation is reprocessed by the clouds. And if we measure the time delay of the cloud answer, we measure the distance between the black hole and the broadline region. We know the temperature, we know the size of the region, and then we can calculate the absolute luminosity of the source. And if we know the absolute luminosity of the source, and then we can measure the observed luminosity of the source, we can determine the distance.
Quasars could open new possibilities in measuring cosmic distances. That is why the Center for Theoretical Physics has become a part of a larger project focused on solving the problem of dark energy and the cosmic expansion rate. Chile is known as the best place for astronomical observations. The Atacama Desert offers unique conditions to gaze at the night sky. It is the reason why Chile was chosen as the place for a new project that can change what we know about cosmic expansion. Universe Scale aims to improve the calibration of the cosmic distance scale. It has won a European Research Council Synergy grant, designed for the most ambitious and complex research initiatives that require people from different fields of science and technology to collaborate. Universe Scale will measure cosmic distances with an unprecedented precision using several different methods. In order to do that, new instruments will be constructed in an observatory in Chile right next to ESO's extremely large telescope. All of this in order to solve the mysteries surrounding the cosmic expansion rate.
This discrepancy shows us that we don't understand the universe sufficiently well. Modern physics is not able to explain the observations, so we need to improve it. One way to get rid of the discrepancy would be to understand better physical nature of the dark energy. We need to measure the Hubble constant with very good precision to understand our universe much better. The main goal of the Universe Scale project is to measure distances to very different objects, starting from the solar neighborhood out to very distant quasars. And we would like to improve several methods which astronomers use for distance determinations, apply them, and determine the famous Hubble constant with a precision close to 1%. big avalanche of data will be available from satellites and big surveys. And in order to use them for distance determinations, we need to complement them with spectroscopic and photometric data. In order to be able to do that, we need new dedicated telescopes. And this is why we established an astrophysical observatory in northern Chile to collect these data. In order to measure the Hubble constant using the classical approach, we need several different techniques because it's not possible to measure distances to all objects in the universe. We need to start with geometrical techniques which can be applied to nearby objects. Then we can use them to calibrate other techniques which can serve us to reach galaxies located much farther away. And then finally we can calibrate long-range distance indicators like supernovae. Altogether, we can measure distances at different locations and measure the expansion of the universe, or the value of the Hubble constant.
What the Universe Scale project aims to discover might revolutionize our understanding of the nature of the universe. Most importantly, measuring the rate of the cosmic expansion at different distances may shed more light on the enigmatic dark energy.
If we really understand the evolution of the dark energy, we can tell more about the future of the universe. If only the cosmological constant works, then the accelerated expansion will continue forever. On the other hand, if it is something else, then maybe there is a minimum value. We really don't know. This is an open question.
The Universe Scale project is a collaboration of scientists from several different institutions, the Center for Theoretical Physics and the Nicolaus Copernicus Astronomical Center from Poland, as well as the University of Concepcion in Chile and Paris Observatory in France. It will provide new quality in measuring cosmic distances, giving the scientists a new, precise tool for studying fundamental mysteries of the universe. The research in the cosmic expansion and dark energy could result in a major breakthrough in our understanding of the origin and the evolution of the universe. That would have a deep impact not only on modern physics, but also on our society and culture.
As you have seen, this movie was created thanks to support of so-called NAVA, Polish agency financing science and scientific institutions. So this is the end of this short ceremony. Thank you, Vladimir. Thank you, Bożena. And now we shall start the scientific session, and Bożena will be the chairman of this session. Chairperson. Yes. Excuse me.
Or chair for short. Well. Anyway, so we will start now the astrophysics session. I hope we have already our first speaker, so I will shortly introduce him. This will be a remote speaker. So Professor Jimmy Wang from Institute of High Energy Physics in Beijing will talk about pioneering research he's doing. He's one of the leading experts in mapping, I would say mapping active galactic nuclei, but his current interest is actually in geometrical distances to quasars based on this mapping. So do we have a connection?
Okay. Hello, Bożena.
Oh, hello.
Hello, can you hear me?
Yes, yes,
okay.
Yes, fine. Go ahead.
Okay, should I start?
Yes.
Okay. I'm very happy to join the celebration of the 40+1 anniversary of the Center for Theoretical Physics. I am very grateful to Bożena and the organizer to invite me for the talk. It was very nice video from Bushina 1 minute ago. It's really related talk today. I think I would be happy to talk about the geometrical distance to quasars using the SpectroAstrometry and the reverberation mapping, which are shortened by a new word, which is called SARM, S-A-R-M. This was done 1 year ago with my collaborators, but we have some new development for the using the more advanced technique. So I will briefly talk about what is spectroastrometry and reverberation mapping. And then we introduced how to do the joint analysis for the gravity data and 2-meter data and the reverberation mapping data from a 2-meter telescope. Okay, finally, we have, I think we have a successful application to the first quasars 3C273 using the 1D and 2D. And then we have a very brief prospect of the SARM analysis for future. So this really breaks through the VLT, the gravity installed on the VLT just opened in the new era of high spatial resolution astrometry in AGN research. So gravity has a very powerful spatial resolution. It can reach 10 mu arcsecond. This is really horrible resolution so far we can get. So the inner structure of the borderline region will be spatially resolved somehow. As shown in the left panel, we can see the borderline region just a gas surrounding the black hole, which are photonized by the emission from the accretion disk. So so far gravity as a pioneering observation in quasars just finished They published 3 targets so far. So it's already show its potential power in the future for determining the cosmic distance of quasars using the geometric method. This is the direct way to measure the cosmic distance, I think. So the principle of the astrometry actually is very simple. When the people are using the interferometer to determine the photon center as a function of the wavelengths, basically depends on the kinematics of the ionized gas, depends on the velocity distribution and the spatial distribution. This can be done actually by Gemini. Actually, I think 1 month ago, there one nice paper published by Americans group using the Gemini telescope. There's an 8-meter telescope to measure the black hole mass using the spectroastrometry. But if we do the spectroastrometry with VLT, that's the resolution will be much powerful than single telescope. So the interferometer will measure the angle phase delta phi, basically determined by the baseline and the wavelengths and the delta x. Delta x basically is the angular size, is the size of the borderline region over distance. So basically, if the borderline region is larger, or the distance, if the distance is closer, so we have the larger delta phi. That will be easy to spatial result. So this is the very simple principle to do, but actually it's very hard because of the atmosphere turbulence. The VLT must use the AO and a very high technology, I think, to do that. They published the first paper in Nature almost 1.5 years ago, the left panel shows very beautiful interferometric signals. They show perfect Kepler rotating disk of the partition alpha because the gravity is working in the near infrared. They measured the profile of the partition alpha, but they also measured the interferometer phase I show here. So the very simple Kepler rotation disk can fit the gravity data very well. So the people generally believe the Broadland region, at least in 3C273, has contained a Kepler rotating disk as the most simplest model of the Broadland region. This is the first Broadland region spatially resolved in the world. I think this gives a very, very beautiful result so far. So the reverberation mapping, however, they measures the time lag between the H beta, the Balmer line or other lines with respect to the continuum, which is the ionizing sources. And so because of the difference of the path of a Balmer line or the emission line with the continuum, so we can measure the light curve. If we focus on the spectrograph with the center on the center, we can measure the continuum light curve, and we can measure the Balmer line, or usually it is H beta, and sometimes if you use the HST or IUE, we can measure the Lambda alpha for the lossy agents. We can see there is clearly time lag. This means that this is the characteristic size of the Broadland region. This is the absolute dimension we can measure it of the Broadland region. So this is a very simple observations. We can do this through 2-meter telescope. This is very, very convenient and very, very cheap. You know, there are a lot of 2-meter telescopes in the world. So the Gravity published the first paper on 3C273. We just finished our campaign for this one using the American Block 2-meter telescope and a Chinese 2-meter telescope in Jian, and we measured the time lag is about 170 light days. Here I show you the light curve. So it is above. This panel is a continuum. This is H beta. We see there's very clear reverberation, but there's a little different trending here. Probably the continuum is contaminated somehow by the continuum emission from the jet, from the relativistic jet, which is very powerful. We can measure. So the H beta size basically is 170. Okay, so the accuracy of the H beta line region is quite accurate, I think. So if we join the two independent data, basically we call this the SARM analysis, we can measure the geometrical distance because the gravity on the VLT can measure the angular size of Broadland region. This is the theta Broadland region. Reverberation mapping can measure the physical size of this is the R Broadland region. Okay, divided the two numbers, we can directly get the geometrical distance. This is the principle. So the advantage of the SARM analysis is obvious. We don't need distant lidar. We don't need to do extinction or reddening correction. We don't need standardization. For example, the type 1 supernovae have to calibrate by the famous Philip relation. But on the other hand, moreover, the aging lifetime is very long. We can repeat to measure them and for the systematic errors. So this systematic errors is very, very easy to test in this way. So all of the advantage are very different from the classical distance tools, C5 or the type 1 supernovae or BAO or something else, or the binary stars, something. So basically, if we do the SARM analysis, we can simultaneously measure the black hole mass. And the accuracy is also very, very high, basically. It's much, much better than the black hole mass measured by the each method alone. So we think the gravity, the SARM analysis is inevitable to do in the future. So just to show you here, basically the SpectroAstrometry show that, because they can measure the angular distribution, and the reverberation mapping basically can measure the radial distribution of the Broadland region. So we need to build up a simple Broadland region model. This is the measurement is model dependent of the Broadland region, but we can easily to observational test what is the Broadland region model. At least we can select some of the aging with the simple Broadland region, something like that, 3C273 with a pure Kepler rotation disk, like this. So the first application to the 3C273 was done by my group with the simple 1D SARM. This means that we only model the time lag. We don't model the H beta profile. So there is a simple, there is a basic assumption. We assume the partial alpha region is exactly same with the H beta region. This is the assumption. This is the only assumption we use. So here I show you the fitting results are quite satisfactory, not only for the gravity data, but also for the Broadland, for the reverberation mapping data. So the distance is 551 megaparsec. The accuracy roughly 15%. And recently, the paper will be accepted by APJ very soon. I think we give up assumption the partial alpha region is the same with H beta. So we code this the 2D SARM analysis because we include the H beta profile in the reverberation mapping data. Usually here is show the different. The width of the partial alpha is different from H beta by roughly by 13%. Actually, this is looks like it's small, but it's quite significant. If we compare with the others, there is a general trend that the partial alpha systematically narrower than the H beta. So this is a very clear. Probably the partial alpha basically is emitted from the same hydrogen atom, but probably the partial alpha has a different optical depths from the H beta photons. So this could be the physics behind. So we apply because there are two regions, two Broadland regions. We have to do H beta region and partial alpha region, and we use the RAM, the reverberation mapping likelihood, and gravity likelihood. We use the MCMC scheme, and finally we get the final result. The advantage here is we assume the black hole there is only one black hole. So this is another assumption here again in 3C273, but we don't know if there are two black holes or even there are binary black hole. We don't know this. So far the data at least is not so accurate, allow us to distinguish there's a single black hole or binary black hole, something like that. So the model, there are different combinations for the Broadland region models. If you assume the R distribution with the two-pole law or with the extended gamma function, so there are two options for the radial distribution, and there are two options for the vertical structures. This is if we assume all of the clouds on the surface of Broadland region, and on the contrary, we can assume all of the Broadland region clouds are located in the mid-plane. And for the trending effect, because continue has a different trending with the H beta a little bit. If we use a single parallel trending, we can basically get the eight kind of the combination to fit all of the data. So the so the gravity data it's perfect, and the Broadland region data, the reverse mapping data is also wonderful, I think. So finally, we found the model 4. It means the Broadland region have double power law, and all the clouds, most of the clouds are distributed on the mid-plane, will be the best fitting of the model. So we show here, so we show the data, the distance, the black hole, the opening angle, and something like that. We found the model 4 has infrared constant, the K is the best for the for the 3C273. One thing we have to stress, the inclination generally from the 3C273 can be estimated by the relativistic jet. This is the radial jet. So probably all the fitting results is consistent with the jet orientation here. So we found that the black hole mass from the 2D SARM is consistent with the Michelson relation. This is a simple comparison here. So the black hole mass is pretty consistent with the Michelson relation we found here. So the second SARM analysis has been done using the same approach by the gravity collaboration that published almost 1 month ago. They measured the NGC 3783 to measure the distance. So they get the distance roughly 40 megaparsec, like here. So I show the number of the archive paper. So in the future, I think the gravity will be upgrade in a few years, probably in 3 years. So they call the gravity plus. So they can get improved in several different, especially they want to improve the sensitivity of the gravity. So far, the gravity just can only detect the K-band magnitude is 10.5 AGNs or quasars. So this the target are quite a few. But in the future, the gravity plus will greatly improve the sensitivity. So they will probably, they claim they can detect a lot of the quasars. They have the extragalactic signs beyond the galactic center. They can measure the black hole mass and the AGNs. So basically, they can detect the quasars at a redshift 2 or 3. So this is, if we can do reverse mapping until the redshift 2 or 3, that would be fantastic. We can directly measure the distance from redshift 0 to redshift 2 or 3. So there are plenty of the target to select. We have to do, we just began to do this. So so far, the only 2 targets had been measured the geometrical distance for 3C273 and NGC 37 and 83. A Monte Carlo simulation show that if we can do 100 AGN up to the redshift 1, the Hubble constant can reach the from 1 to 3% level. So basically, the Hubble tension could be explored in this way, especially we can measure the distance and the Hubble parameter versus the redshift. Basically, this is the Hubble diagram. So we can measure cosmic expansion history of the universe. So thank you very much. I end here.
Okay, thank you. We have now time for questions.
Yes, please.
So maybe I will start with the first question. So your method is complementary to the method which we will try to use in this ERC grant. We plan to use just continuum time delay, which also offers the distance to the quasar directly without any ladder. Probably we should plan to use more or less the same objects as they will be studied with gravity, and then we can compare the distances to the same objects. Could you comment on that?
That would be fantastic, I think. Yes, I think so far the gravity study is just began to do this. I think there are a lot of, I show you here a lot of target to do, but if we do the high Z quasars, I think that would be great. I think definitely I appreciate, Bushina, if you continue to measure the quasar distance, that will be, that will uncover all the mysteries of the universe. I'm looking forward to see your data.
Okay. Other questions? Already here. Mm-hmm.
Thank you for the talk, Mariana Haber. I was wondering, in this plot that you're showing here for the HZ, you've got this measurement at redshift almost 2.5, and these measurements, if I understood correctly, are not depending on a cosmological model. So this is kind of, unlike CMB extrapolation points. So the error bars that you have here, what would you need in order to shrink them? In other words, are there systematic dominates, there are statistical error bars?
Very good question. Actually, this plot on the upper panel is not from my paper. This was done by the VAO peoples. I just show you if the quasar distance can be measured for in next, I think in the next few years by gravity plus, that we can get the accurate enough history of the expansion. So on the other hand, if I understand your question correctly, so far the systematic error bars from the gravity from the SARM analysis is open. So we are doing to determine what is the systematic error bars. The error bars I show here just probably is just the measurements error bars. So we are not very sure, but basically the advantage of the SARM analysis is the systematic error bar can be done by reverberation mapping. So we can show you the Broadland region, some of the quasars has pure Kepler rotation disk geometry. So this will be a perfect Broadland region for the distance measurements in future. So there are a lot of work to do, not only for the high Z, but even in the local, there are a lot of things to do.
Okay.
Yes, thank you.
Vladimir, you had a question?
Just a specific question about when you mentioned the inclination measurements in 3C273. Just a question whether it is somehow constraining the possible warping of the system, so that there would not be actually the unique value of this inclination, or it's negligible?
Very good question. This is, I think, a very professional question. This, so the whatever gravity measurements, gravity data, or the reverse mapping data, the inclination angle I and the opening angle of the Brownell region degenerate together. But if we do the sum analysis, so the degeneracy will be much lower somehow, I think. So the result I show you here from our paper exactly almost the same with the relativistic jet. So this is the model some parameters degenerate, so we can decouple the degeneracy by the sum analysis, because gravity gives the angular distribution of the clouds, and the reverberation mapping reveal the radial distribution of the clouds. So if we combine the two data, we have the global geometry and the kinematics of the Brownell region. So this is the advantage why we should, or this is the only way, or the unique way to combine gravity and the reverberation mapping data.
Okay, Swayam, your question?
Thank you, Professor Wang, for that wonderful talk. I have a two-part question. The part one would be about this broadline region model that you mentioned. So in this SpectroAstrometry reverberation mapping, you do say that, and you figure out that the Paschen alpha and the H beta emission tend to differ by themselves. So is there now a self-consistent BLR model, which is kind of going to be a new model with respect to the existing ones that we have? For example, the failed will scenario and the ones of the collapsing model. So that would be question number one. And the part two is in the context of measuring time lags in reverberation mapping, we do have different methodologies and algorithms that do sometimes differ by themselves. So would you like to comment on the one methods which are really going to be self-consistent with themselves? Thank you.
These are really two hard questions. Many. This is Panda from Panda, yes?
Yes, Professor.
Okay, so actually, we so far we just using the physical model, which can be tested by reverberation mapping itself. We have 10 years data I show you here. This is the left lower panel is show here. This is really good data. So the data show the information we have only for the Paschen alpha. It's only the Paschen alpha profile. So except for of course except for the gravity data, but we don't have the H beta data. So if you calculate from the photoionization somehow, probably you can produce something could be different from the simple model. But so far so Dupu, probably you know the name, we just want to do some theoretical calculations to check if the photoionization model can really match the two observations, the gravity data and the reverberation mapping data. But on the other hand, if we do that, we have to include the ASM for some energy for some radiation transfer in the Brownell region. This is more hard, I think, so far. So there are a lot of things to do. What I can reply your question just like a few words like this. Okay.
Okay, I think we have to move on, so let's thank our speaker again.
Thank all of you, my Polish friends here. So take care for all the people in the pandemic time.
Oh, well, we were brave enough to have a conference in real space, right? Congratulate us and hope for the best for the future. We will survive, I guess. Okay, Agnieszka. So our next speaker is Professor Agnieszka Janiuk, who will talk about stars, black holes, and gamma ray bursts. There is a misprint in the written title. That was why I was confused. Bernst? Of course, gamma ray bursts.
Yes, thank you, Bożena. And it's very nice to see all of you here on the very last day of this conference, and it's very nice to give a talk live, in front of the people. It's been a very long time since I done it, so excuse me if I'm not very fluent in speaking, because it is very much different than speaking to your own screen via Zoom. And let's try. So the title of my talk is Stars, Black Holes and Gamma Ray Bursts, and the painting in the background is showing cosmos. In this painting, there is a lot of chaos, as you can see. So cosmos, in my mind, is a chaotic thing, although from the linguistic point of view, the Greek language says that cosmos and chaos have opposite meanings. Well, the Greeks probably imagined the cosmos to be very ordered, well-organized entity. What we know is that it is, in fact, full of transient, violent events and a lot of explosions and things that are happening there. And we try to understand, but we are still very far from the final answers. So I started my career in the Center for Theoretical Physics actually 11 years ago. I think 2010, October was my first day. I moved there from Copernicus Astronomical Center, where I did my PhD, and then tried to move to another place to get some independence, maturity. I hope Professor Sarna, who was speaking on the beginning of this week, will be happy with this, at least that I tried. The two very fundamental branches of physics that are also the foundations of the Center for Theoretical Physics here in Warsaw are quantum mechanics and general relativity. Both of them are very important in astrophysics because they describe stars in the very last stages of their evolution, at least. They are very important science foundations to describe neutron stars, white dwarfs, and black holes, which are formed after the stars exhaust their fuel. When the thermonuclear fusion is not going inside the stars, the thermal pressure cannot support the star against gravity, and the star is going to collapse. What prevents the collapse of the star to the black hole is the pressure of degenerate neutrons or electrons in neutron stars and white dwarfs, respectively. I'm sorry that this figure somehow moved, but actually it shows the idea of the degenerate state of matter from the Fermi principle. But the scientists who derived first the conditions for formation of the neutron star and the white dwarfs, and first person who considered this physics was Subramanian Chandrasekhar, who derived the maximum mass of the white dwarf. The maximum mass of the neutron star is actually not precisely well known. We have some tight constraints on that, but still no more than 3 solar masses is able to be supported by even the pressure of degenerate neutrons. What is heavier, everything what is heavier inside the star forms a black hole. Here in this cartoon you can see the end products of stellar evolution as we can understand them now. Of course, the evolution of a single star is not observed by any astronomers or by any methods that we are able to use, because of the lifetime of the star is very long. But we have the data about numerous stars in their different stages of the evolution, and we can also solve theoretical models, numerical models, solving the structure of a star that is described by differential equations with proper boundary conditions, and hence we can, using computer models, we can understand how the stellar evolution proceeds. So here you see the two paths that are leading to the formation of a compact remnant. The average star, so low mass star, typically ends its life as a white dwarf. The massive star goes through the stage of a red supergiant, then explodes as a supernova and forms compact remnant, either a neutron star or if it is heavier, then we have a black hole. So yeah, about the very mechanism of the supernova explosion, there is of course a lot of work being done now in astrophysics. So basically things that are understood a little bit now, that this explosion is driven by bouncing shock formation. Finally, the energy is removed by the neutrino-driven winds. Most of the stellar envelope is being expelled from the core, and the remnant of the collapsed core stays here. Where is this mass gap between the black holes and neutron stars? It is a little bit tricky to understand. What we can speculate on is that the progenitor mass, of course, is very important, the mass of the star on the main sequence, but not only that, also some metallicity influence is probably very important here, and also the evolution of the star if it is having a companion. You have to remember that most of the stars in the universe, I think more than 70% of the stars are not single stars, but they are living in multiple binary or triple or hierarchical systems. And this evolution is then driven not only by the evolution of components, but also by the mass transfer and episodes of the common envelope. Okay, but this is kind of one of the channels, yes, to form a black hole. The other important channel of black hole formation is the merger of two compact stars, namely two neutron stars or neutron star and another black hole, whatever, two compact objects that merge together, and their product is more massive than the allowed mass for the neutron star. So they may form the black hole after the merger. During the in spiral phase, gravitational waves are produced, and this is what we know since the Einstein's theory that gravitational waves are predicted by general relativity. Also, Poland had important contribution in the works by Professor Trautmann, for instance. But finally, they have been observed only from 2015. Yeah, the gravitational waves are these transverse deformations of the space-time curvature, which are propagating with the speed of light, as theory predicts. And the source of these gravitational waves are the masses moving with acceleration. And observed proof of this was finally found in 2015. The Nobel Prize was given in physics for that discovery to basically 3 scientists, but actually a very large group of people worked on discovery of the gravitational waves because first of all, it was needed to build huge instruments to be able to observe them. So 2 famous gravitational wave observatories are now operating. They are having subsequent observation runs. Yes, the LIGO interferometer located in the United States. The 2 observatories are apart from each other by 3,000 kilometers, and the Virgo detector is located in Europe, in Italy near Pisa, and also Poland has some participation in this Virgo project. All right, but well, we observe these gravitational waves. How it is done precisely, we have to know what the signal should look like. To somehow understand if we see really the signal or we see the noise, we need to have a pattern. Yes, and to produce this pattern, actually numerical relativity is being in use. So the numerical relativity methods are the methods to calculate how the theoretical gravitational waveform would look like after the merger of two compact stars, for instance, two black holes of a given mass and given spins. This problem is a two-body problem in general relativity, is not having any analytical solution. So we need to have the numerical methodology to do this. And actually, the first, sorry, I see there is a lot of problems with the text here, but all right. Yeah, a little bit missing, yes. It's actually here was also, I wanted to mention the works by Pretorius and Manuela Campanelli from 2005, 2006, who were the first people who developed numerical methods that are solving the motion of black hole binaries and can somehow describe or solve for these technical things that we have to deal with in numericals because of the singularity problems and the black hole horizon findings. All of these methods are now being available for users, so if you want to make a simulation, you can have the codes which are using adaptive mesh refinements and allow you to evolve your favorite binary system until the state where it merges and produces the gravitational waves, as you could see in the animation just a minute ago. So yeah, this is the first ever detection of the gravitational wave that was done in 2015. The source name is GW150914. These were two black holes. And the event was measured very precisely on 14 September 2015. 2016, there was a press release, and we had this pleasure to see many more of them later on, since LIGO and Virgo are operating. So you see here, like the 3 of the black holes which have been observed by gravitational wave observatories. These objects, small, are merging, and we observe the most massive black holes that are now in the catalogs are about 80 solar mass. And the components who are merging together to form them are actually mostly heavier than 10 or 20 solar mass, but some of them recently have been found to be smaller. Anyway, there is another, of course, old and very traditional method to find black holes in the universe, and we observe actually the stellar mass black holes since 1960s when we had first X-ray satellites operating. So what we see in X-rays is the emission from the matter in falling to the horizon of the black hole. We do not see this very black hole by itself, but we see the light emitted from the matter on the cost of gravitational potential energy. So we see the accretion disk. We can model the spectrum emitted from such a disk and distinguish its components, and we can say something about the both mass and the spin of this creature that is swallowing the material from companion star. Here you have depicted the artistic view of such a binary system, and we know it. There's many examples of such systems in the universe. Well, single black holes are being observed actually also since very long time, since we discovered quasars. Bożena is a specialist for quasars, and here is actually the slide which I borrowed from my old public talk, which was more than 2 years ago. Just before the pandemic started, I gave a public talk in Copernicus Astronomical Center. It was in 2019. In March, very next day we had the lockdown. So now I'm using the slide to also show you how maybe it is worth to tell the public about how we observe these black holes. Well, we do not see these black holes by themselves again. They are single, they swallow material from the surrounding, but they can also eject some material, and here's the jet. And similarly, if we do not see a dancer on the stage because her skin is dark and is not shining, yeah, by itself, but we see something that she can throw out. So, for instance, the scarf or some material, and we can have this analogy in mind. Yeah, so we observe these jets from accreting black holes. How do we understand the jet production mechanism is something that many people work on at the moment. So presumably there needs to be an accretion disk around this black hole. There needs to be a rotating black hole. Most probably fast rotating black holes are powering these jets on the cost of their rotational energy. And this whole mechanism has to be mediated by the magnetic fields. Yeah. This is like general understanding. We can do, of course, simulations to really model this on the basis of some equations of physics. And we can use numerical simulations. We can use big computers to produce such jets, to understand the accretion process and physics of accretion onto these compact stars. And of course, we confront our models with various observations possible through the X-ray, through the radio, and finally through the gravitational waves. So now in this second part of my talk, I want to just briefly tell you a few examples of the works that have been done within my group and in some collaborations since I started working in Center for Theoretical Physics. To show you, like, review. Yeah, I'm not going to tell many details about any of these works because I couldn't decide if there is any single work that is most important for me. I think all of them are in some sense important, also because of the people with whom I had the pleasure to work. So here is Magda Kunert-Bajraszewska from Toruń, Nicolaus Copernicus University. She habilitated a few years ago, and she's a great specialist in radio astronomy. So what she did, she found actually the system of two quasars. One is the radio quiet source here. The second one is a radio loud. This one is then the core of the active galaxy. This one is inactive. And what we understand is they are about to be merging. Well, about to be merging in the quasar time scale is quite a long time before they really merge, these two black holes. But we think that we found this cosmic collision in the action, and the work with Magda was published in 2011. Then another work that I want to mention here is simulations of gravitational waves and gravitational recoil effect, actually when the black holes are merging. Yeah, the product of the merger is going to be recoiled by the force, yeah, that we obtain thanks to the momentum conservation. So these two black holes on the orbit are actually merging. One of them is smaller and spinning, the other is larger and non-spinning. And this effect we simulated using computer simulation. Well, we wanted to address actually the question if the merger of two black holes can have any electromagnetic counterpart. Well, if it is in vacuum, then of course not. But if it is not in vacuum, then maybe we could have some electromagnetic counterpart. For instance, if the merger occurs inside the cloud or stellar envelope, if that is triggered by the collapse of one of the stars where the black hole is being formed in the core. So this binary, the famous one, the first discovered one, 150914, had apparently no electromagnetic counterpart, at least that was claimed by the integral satellite, X-ray gamma ray satellite team. But some rumors were spread that something was observed. Yeah? So we still have in mind the idea if we can have like a scarf, okay, or something being ejected by this dancer, one of these black holes, and we could observe some jets emission. We want to work on that maybe in the future, but what is actually more reliable, yeah, and more appropriate to give to students. Okay, 5 minutes, so I'm going fast, yeah. And these were the accretion disk models and coronal flow models done using computer simulations. Here is Mikołaj Korzyński, my first PhD student at the Center for Theoretical Physics. He did very nice PhD thesis in 2018. And this is a sample of his work, the limit cycle oscillations of the accretion disks. Also, Petra Sukowa, the postdoc hired at CFT, worked on the oscillations. In this case, there was oscillations of the shock position, so transonic flow onto the black hole, quasi-spherical, was modeled with numerical methods and very nicely represented the observed behaviors of the accreting black holes. The projects are being continued. Now Ishika Palit, who is here, and she has a lot of details about this project in her poster downstairs. In the poster session you can see, she did hydrodynamic simulations of this shock bubble evolution in 2D using the GR hydrodynamical simulation. Here another student, Dominika Król, this year we published a paper where she did also GR MHD simulations of black hole accretion using the code that is actually capable of evolving the mass and spin of the black hole during the process of collapse. This process is actually very important for gamma ray bursts because if we consider long gamma ray bursts produced by the collapse of a massive star, we really start from a small and even maybe non-spinning black hole, but we add both mass and angular momentum to this black hole, so the black hole evolution is actually important. So there are a number of works also devoted to the central engines of these gamma ray bursts. We considered the microphysics, the composition of this dense and hot matter in the center of the gamma ray burst, because actually what is important here is this accretion rates are very huge, so the matter is prone to the nuclear reactions, and it's cooled by neutrinos. This work was done first work with collaboration with Monika Mościbrocka, and we also studied jets produced by these central engines of gamma ray bursts with my second postdoc, Kostas Sapontzis. He modeled the energetics of jets and energy extraction from the rotating black holes in big detail. Yeah, as I mentioned, these accretion flows are very hot, very dense, and also there is a lot of composition changes in terms of nuclear physics. So we need to actually understand how the flow and outflow jets, either jets or winds from the accretion disks, are composed, if there is a possibility of producing elements heavier than hydrogen and helium, because this is what has been observed. Maybe I will show you the observed data for the kilonova. This is another very famous object, GW 1708, the measure of two neutron stars in this case. They merged together, formed a black hole, and what was observed was the gravitational wave emission, hence the name of this object, starts with GW. But also we observed here accompanying gamma ray burst, and we observed here accompanying light curve, the kilonova light curve. The kilonova is something less energetic than a supernova, but still very energetic. And the mechanism of emission of the light is also similar, because this is powered by the decay of the heavy radioactive isotopes formed during the process of the merger of these two neutron stars. And also these isotopes, actually, as I can show you now here again, can be formed in the very engine of the gamma ray burst, yeah, this accreting black hole and its wind produced from the accretion flow. All right, so we are doing the simulations of the R-process nucleosynthesis. Here, R-process means that rapidly subsequent isotopes capture neutrons. They capture them faster than these neutrons are able to decay via beta decay. Hence, we can produce elements until like 180 on the Mendeleev table, and we can populate the universe with the heavy ions. Okay, and finally, these simulations of the magnetically arrested accretion modes. We started this with Kostas Sapontis, the postdoc who was here for couple years. He worked at CFT in Warsaw. Now he's back in Athens. But we still collaborate, and we have some kind of joint supervision, if I may say, but formally I'm the supervisor of Bestin James, who is a PhD student here. And they simulate magnetically arrested accretion modes in the process of formations of jets. So this is very highly magnetized matter, which is able to launch along the axis of rotation of the black hole these very energetic and magnetized outflows. We are doing the 3D simulations. So this is the movie prepared by Bestin recently. The movie, I think it should show, how the jet energetics parameter, so it is a total energy of the jet in terms of the sum of the thermal energy and Poynting energy. So from the magnetic field is expelled. Here is the engine. Jets are bipolar, so in two sides from the black hole. And you see here variability also is very important feature that we can actually directly compare its timescales and amplitudes to the observed gamma ray light curves from the gamma ray bursts. All right, so that was the end of the talk. Almost. I mean, I just want to acknowledge and say thank you to all my group members. So we currently have 2 postdocs. Fateme, she arrived to Warsaw to CFT last year, and Przemysław is just hired 3 days ago, but he's already here at the conference. We have currently 2 PhD students. Ishika Palit is going to defend her PhD thesis in 2 weeks, and she is presenting a poster here. We have Bestin. Bestin is now in India, but he will come back in a couple days from vacations. Of course, he deserved after this pandemic to go back home after 2 years of staying in Poland in the lockdown. And Michał is doing the bachelor's project in our group on the neutron stars. He's going to start this project in October with us. So let me thank you very much for your attention. And of course, I would like to invite you to any of the next conferences that we hope to organize. This one had to be postponed, unfortunately. RATOP, Relativistic Astrophysics Theory and Observation Perspectives. The title is huge, but the acronym is also kind of typical, yes, for relativity and astrophysics. But we had, kind of interesting and fruitful conference this year. Thank you.
Thank you. Questions to Agnieszka?
So Agnieszka, actually I haven't understood the story about analogy between a collision of 2 black holes and electromagnetic fields. Were you looking for such signals from electromagnetic signals that would be mistaken or similar to the signal of gravitational waves?
No, we would like to look for signals that are accompanying, and they are spatially and in time correlated with this gravitational wave source. Most probably the electromagnetic counterpart is going to be faint, yes? Hence, up to now, we missed such signals. Or maybe they do not exist, but it's hard to imagine that all these black holes that are merging are really in vacuum. There must be some remnant matter. For instance, if one of these black holes is just newly formed after the collapse of the star where it was born. Or there is some interstellar material. Or there is an accretion disk, black holes merge inside the disk that is the center of the galaxy, whatever. Yeah, so we need to search really for the counterparts in electromagnetic waves to the gravitational wave signals. We hope to have more data, and we hope to have better algorithms also to find such correlations.
Okay, thanks.
Okay, let's have one more question.
About your or magnetohydrodynamic modeling of jets, do you see in the context of Ernst Mach also the effects of frame dragging or rotation or effect of the rotation of the black hole on jet production?
Well, basic effect is the power of the jet. Yes, the more rotating black hole up to the maximum Kerr spin of the black hole, the more powerful the jet. This is the Blandford-Znajek mechanism.
Yeah, and you can somehow see it monotonically. I mean, growing all the time with increasing spin.
Well, quadratically, yes.
Or quadratically, but
yes,
growing.
Yes, growing,
yeah.
of course.
I guess we have to move on. So thank you, Agnieszka, again. And the last speaker of this session is Dr. Katarzyna Małek, who will tell us about from pie of the sky to LSST.
So first of all, thank you very much for having me here. It's a huge pleasure for me to be here. But not only, I have to say that today at 4:30 in the morning I woke up and I realized that I'm giving a seminar in this institute again. So you have no idea how was it during 10 years when I was a member of this institute. Each seminar was a little bit, stressful. So yeah, so I'm sorry if I'm okay. I think it's okay. So I hope this time I will be, more calm and I can explain you what I'm doing now. But first, I would like to say a few words, not only a few words. I would like to say a little bit more about one of the project which we had in CFT in the Center for Theoretical Physics. First of all, it can be a little bit surprised that when you think about it, that the member of the institute, the physicists, decide to build a telescope, a robotic telescope in Chile. It was Lech Mankiewicz who decided to do that with his colleague. And so this is the slide I showed last time, 10 years ago, during my defense. And it's nice to go back to your old slides to show something. So the Pie of the Sky collaboration it was made of some institutes. Here I put the main names, which for me they are main names in this collaboration. And as I said, Professor Lech Mankiewicz and Professor Grzegorz Wrochna, they decide to build a robotic telescope. To do some science. I will tell you which one, which science. And also during the time also Professor Żarnecki decided to join to this group. Okay. The scientific motivation of building the robotic telescope in Chile was to find the optical counterparts, so this electromagnetic spectra from gamma ray burst. So Agnieszka already said a lot about gamma ray burst, so I can just make a nice to show nice pictures and I'm not going to go very detailed in the subject because I'm not working on the gamma ray burst anymore. But what Pie of the Sky wanted to see, it was to see the optical counterparts of gamma ray burst in the same moment as we can see gamma rays from escaping from the central aging. And you can think about those gamma ray bursts as such a violent phenomena. So they are extremely energetic, but also the duration of this phenomena is just a few seconds to thousands of seconds. So it's extremely violent, but not very known phenomena, especially in the time when I started to my master thesis. But also, of course, because it's the gamma ray burst is characterized by very short time scales, so also any other variability on the sky we are looking for. So when I started my work with Professor Mankiewicz, we were thinking about gamma ray bursts. As you know, we have the central aging, which was caused by, for example, 2 neutron stars or 2 black holes. This is the picture I had in my slides 10 years ago. And then something happened, and from the central aging, we had this huge burst with gamma rays, which can be observed. But then we have after some time, we were thinking about some collision of those gamma rays with interstellar medium, for example. And then we were thinking that then the afterglow, so the visible light and other wavelengths are made, yes. But we really wanted to know if the scenario looks like that. So maybe we have already the optical counterpart here, but nobody ever looked at those at this moment on the gamma ray burst. So this mysterious center engine, we knew about it just because of the observation in gamma. But of course we could easily check the place on the sky with other instruments, but we didn't know where to look, in which place on the sky. Even though the gamma ray bursts are not that rare, we can observe a few gamma rays per day probably now, and but nobody knows where the next gamma ray burst is going to happen. So the very clever idea to look everywhere all the time, to find somehow to be lucky to find the gamma ray counterpart was, I think, brilliant idea. It was taken from Professor Bogdan Paczyński. So to use very small robotic telescope, not very expensive, and just to monitor the sky all over the time. And yes, so Pi of the Sky decided to build the telescope. The first one you can see here is the prototype. It's my favorite one because I worked only on that one. So it's fully autonomous robotic detector in Chile, and it was built in 2004, if I remember correctly, yes. 2004. The telescope, which it's not very professional telescope, you can see there's normal lenses, Canon lenses, was scanning the sky during the night. So it was taking like 3,000 frames, was 25 gigabytes of the data per night. It was a lot. It's still a lot, I think, but it was a lot during the 10 years ago. And we also had the real-time analysis. It was prepared mostly by our colleague, and so we were looking not only for the information that, oh look, that yesterday especially at that time something happened on the sky, do you have frames to check it, but also we had our own trigger to select new phenomena on the sky. And so the telescope was installed in 2004 in Las Campanas Observatory in Chile, and you can think that it's this one, very nice, but not. Our telescope is here in this small dome, which is a little bit bigger than Mule here, and we did really a lot of science with that telescope. Later in 2011, we moved the prototype to other location, and but it was the same telescope, the same sets of cameras. So as I said, we had only two Canon lenses, two cameras with 2 CCD, 2045 2 times 45 pixels. 1 pixel is about 36 a second on the sky. We had some parallax system, but the field of view was large. It was okay. Okay, so, and with this very nice telescope, you can think about a toy telescope. we did a huge discovery. So what you can see here, it's really the counterpart of gamma ray burst, which and the field we observed just before the gamma ray appeared, during the time, and after. So it was the first. It was a very bright gamma ray. It was also called the naked eye because it was 5 magnitude, so we can easily see if you just had we were lucky and just look at the sky, but it was a northern hemisphere, so we were like double lucky. You could see this counterpart of gamma ray burst by yourself. And I found a slide from the seminar I gave a few days, 6 days after the gamma ray happened. Of course, it's in Polish. I'm very sorry. I just wanted to say that I'm proud of myself because I did it as a diary. So I said that we found the gamma ray satellite found the new GRB, the first one, which was called A. And all the telescope, the ground-based telescope, moved there to observe this gamma ray burst. But then half an hour later, the new GRB happened, and it was in our field of view. And I said that our prototype is crazy. He doesn't know where to look like and in which point of the sky to look. And I got the text message at 8:20 that we have the GRB, but I just was on my way to go to the institute, and I sent an email. But I went directly to the CFT for the seminar of Andrzej Dragan. So yesterday I discussed with Andrzej Dragan about that, and he said, "Oh yeah, I remember the seminar. It was the seminar when all the professors were very nice to me." So, so now you can imagine why I'm stressed now. Okay, so our observations were they changed a little bit the view of our understanding of gamma ray burst. So you can see here, this is the gamma ray detection from 2 different instruments, and here from the very beginning you have the pie of the sky detection as well, and then Tortora, another optical telescope. Then we have some X-rays, radio, and etc. So thanks to our observation, thanks to this toy robotic telescope, we found we uncovered some mysteries of this of the central aging, and we found, for example, that both the optical wavelengths and gamma were produced in the same time, but from different the same place, but with some different mechanism. Okay, so from that picture, when we had the central engine gamma ray and then afterglow with optical, we changed to something when we have the optical and gamma ray bursts in the same time with 2 different cones. And our results were published in Nature. Okay, so then, because of these huge results, we built the final detector, which was then moved to the observatory close to Huelva in Spain. And it was the time I was not working in Pie of the Sky anymore, but Pie of the Sky again found the optical counterpart of gamma ray burst in 2016. You can see it here. And you can think that nice, now the everything will start and we can have more science and more very nice background that you can see. Here you have the Milky Way, here you have the meteor and the comet and a bunch of spy satellites probably. But unfortunately in June 2017 it was a huge fire in Spain, and unfortunately our detector died. You can think that, okay, so it was 2017, you can do nothing. We still have some data, but we are not operating anymore. And but no, we can still do the science based on that data. And last year, Lech Piotrowski published a paper in Physical Review Letters, giving some limits for heavy objects, heavy compact objects in the universe. And because it's not exactly my work and my field, so I'm not going to go very in detail. It's something that Lech gave me. So what you can see, so these heavy compact objects, we think that they exist. They could be, produced in very early universe and travel to our time, and they can produce some light tracks on the sky. And taking into account that our field of view was rather large, we could really analyze limits. If first of all we could check if we have any tracks from those heavy compact objects, but we didn't find. But at least we could give from Lech Piotrowski point of view, the best and the only limits for those objects. And then also other things. So as you can see, it's not the experiment is not dead. As we have the data, we can still use them and we can still do the science. So I think it's amazing achievement of also the pie of the sky, also the institute, that we had this instrument in our hand. And the Spy of the Sky was a natural candidate for the LSST collaboration. And now we are going a little bit into the future. And so LSST is going to be run on this Vera Rubin Observatory, which is very close. It's a coincidence, very close to our previous prototype in Chile. So it's the first thing that why it can be joined together, but of course not. It's the picture from July 2021 of this Vera Rubin Observatory, and on the Vera Rubin Observatory, it's going to be started the legacy survey of space and time. Is going this survey is going to be run for 10 years, observing billions of objects, but this time probably billions of galaxies, in pie of the sky billions of stars. And also the LSST will have something which we don't have in the normal survey, so it will have additional component of time. So we are going to scan the whole sky with some periods. Like I don't remember now. Probably it's 3 days, the main area, but I'm not sure. So again, as with pie of the sky, we have some scans of the whole sky, with some periodic observations. This time the camera is much bigger. I'm not going to say a lot of details about it, but this is a big telescope, and it's going to be fully operated very soon in 2000. We have something which is called this critical path, which is going to be fully operational in 2024, so very soon. And as I said, we have billions of objects, probably a new discoveries, so it's something similar to pie of the sky. And I think that if the pie of the sky still exists, it would be a natural follow-up for the LSST triggers and to follow up the observation from LSST. So LSST, we have the consortium, LSST PL consortium. We have a few institutes and around 20 affiliated members, and so similar as in pie of the sky again. And the main science groups are here for the LSST with the galaxies, dark energy, active galactic nuclei, strong lensing, and informatics and statistics. Those are groups with Polish members, very active Polish members, and we have 5 official PIs for LSST. It's Bożena Czerny, Maciek Bilicki, Wojciech Helwing, Adam Zadrożny, and myself. And it happened to be that Adam Zadrożny was also in Pie of the Sky. And here is the simulated sky and the LSST telescope. So you can see that it's okay. And it was the very long introduction, and now I will say something about these days. So during my career, I observed stars with Pie of the Sky. Then I moved to other project. I observed galaxies in the infrared colors, so very dusty objects. And now I'm thinking about the balance between both of them, between stars and dust in galaxies. And it's okay. I think I lost a part of the slide. It's okay. So it's extremely complex interaction, because for stellar part, you have different kind of stellar populations. You have also the AGNs. You have blazars. You have some dust growth, dust evolution, and everything. And you have to put everything together to see how they can balance in one galaxy. What I'm doing is something different than Bożena or Agnieszka. I'm working on the photometric data, so broadbands. So here you have the galaxy, the spectral energy distribution of galaxy with different wavelengths, and I have some measurements with from different part of the electromagnetic spectra. And what I'm doing, I'm modeling the whole galaxy, having taken into account all models we have for the star formation history, for the dust growth, dust attenuation, dust emission. I'm also including AGNs. So from those, this is one galaxy which was taken in different wavelengths. So what I'm taking the information from each wavelength to model and to estimate the main physical parameters of those galaxies. So, and I have an information about the stellar population, about the dust, the hot and the cold dust, and I can also measure the direct star formation rate, so how fast the galaxy grows new stars. But as I said, I think what I have to do, I have to find a balance between stars and dust, because stars are produced in, we call it the bird clouds, but they are surrounded by the dust. So part of the energy which is produced by the young stars is also emitted. It's taken by the dust and re-emitted in the infrared. So this is the part I want to understand in the galaxies. So. Okay, so usually without dust attenuation, there's something which is balancing the dust and the stars. We should observe something like that here, like the full energy. But because of the attenuation, part of the energy is moved to the different part of the spectral energy distribution, and we have to think about how many energy from the stars is moved to the dust part. Yes, and we have to model it somehow. And because I'm not analyzing single galaxies, but what I'm doing, I'm working on the huge surveys with thousands of galaxies, so I have to do it in a statistical way. So I'm working with the galaxies with a lot of photometrical measurements from ultraviolet, which can reflect the stars, till far infrared for the cold dust. And my last work, I was involved in Herschel Extragalactic Legacy project, when we had millions of galaxies with very nice measurements, so I could play a little bit with them. And what I found, that with all the laws we have for the dust attenuation, like we have the 3 main attenuation laws, we cannot produce in statistical way. Okay, we cannot produce the basic parameter of the galaxy, which is the stellar mass. So it depends on the different assumption. We have different stellar mass, and this is something I really want to measure, to find a solution, how to find the best attenuation law to describe the average galaxy. I checked that different laws do not change really the attenuation, the far infrared when we have those young stars, but change the near infrared part of the spectrum, and we have this mixture of stars and dust and different dust geometry. So this is more complicated. And of course, if I know that I can change easily the stellar mass of the galaxy, so those relation, like for example, we call it like make sequence, the relation between stellar mass and the star formation rate, it's not main anymore and constant, because I can change it with different models used to model my galaxies. And again, I don't know what happened with it, I'm sorry. So we did with my PhD student, we did some simulation for LSST data, and we simulated from the real galaxies, we simulated LSST observation from different period of LSST runs. And we found that for normal galaxies, we are not able even to produce the star formation rate. So what we obtained, it was the star formation rate like that, which we should be on the 0 here. This is the real one. And with including additional models and additional relation, we were finally able to find a good relation. But it means that with LSST we have to, because we want to do with LSST a lot of amazing science, but we have to find a way to obtain the main physical parameters of the galaxies we want to use for the science. And because I'm playing with the dust and stars, also with second PhD students, we also check how this attenuation law can influence the separation between star-bursting galaxies, so the galaxies which are really active with star formation, from those which are like normal, usual, and a little bit boring. And we also know that galaxies evolved, that the whole universe evolved. So, of course, the dust attenuation law, how the energy from stars is attenuated, also should evolve in the universe, and maybe we can use the LSST to reply for this question, as we have this additional time component, which I really liked in Pie of the Sky project. Yes, so my main goal is to measure this dust attenuation. How does it form? How we can evolve, and what are the boundary conditions to use different laws? And this is my team. We are working together. It's a very, very good team. I'm very happy, and I think that also I'm lucky because I started with a very good project, and each project I'm joining or I'm leading, it's very very active and friendly. So to summarize, we don't have a universal attenuation law. We can produce different stellar masses using different attenuations. The geometry plays roles. We know that, but also probably the time. So we want to check it in the LSST. And yes, we are waiting for LSST to make new discoveries, and it's just the pity that we don't have a Pie of the Sky to do the follow-ups. And that's it. Thank you very much.
Thank you very, very much. Immediate comment. You said in your summary that you do not have yet the universal attenuation law. I would bet it does not exist. You shouldn't even try to have it, because physically it's really a problem of a chemical composition, of selective formation and destruction of dust of different composition and size. So yes, forget it. No.
Yes, but if we can find the boundary condition to find to use different attenuation laws, maybe we can use it in more, clever way than we are doing now for this huge sample of galaxies, the statistic. But that's true, I completely agree.
Yes, so you have to rely on a range of attenuation laws or something if you want to parameterize it.
Yeah.
Okay, yeah.
Very interesting talk. I am very proud for some reasons. Could you show your slide from your presentation, your PhD defense? That was the first or second or something like that.
Yeah.
I want to point out something related to Center for Theoretical Physics.
Almost there. I'm sorry. A lot of slides.
Look, what you see there, what you will see there is 3 seniors, basically. That's Grzegorz Wrochna, Aleksander Filip Żarnecki, and myself. There's, of course, Paczyński in the background, who motivated us very strongly and actually gave us $10,000 for covering costs of construction of this equipment from his own ground in Princeton, and a bunch of very good young people, extremely good young people. Actually, most of them are now in the middle of their impressive research careers all over the world. One of them is in Australia, Małgosia Siódek is in Spain and looking for the next place. Kasia Małek is in Warsaw. Lech Piotrowski spent many years in Japan and has just returned to Warsaw University. Grześ Kasprowicz is an eminent authority in electronics related to hardware which is used in laboratories that studies setups for quantum computers. So that's a very specific for Center for Theoretical Physics. I don't know whether, I haven't spent all time at the conference, so I don't know whether it has been mentioned, but actually young people have been and are in the center of our focus. And I hope it will continue like that, right? Research projects which attract the best minds somehow available around, best young minds, and help them to establish, to grow up and to start their careers afterwards. This is a landmark of this institute. I am very proud of it, really. Thank you.
Yes. But perhaps still there is one more comment or question. Yes, Swayam.
Thank you, Kasia, for the amazing talk. Maybe very naive question in the beginning. So what is going to happen with the Pie of the Sky instrument, which was located close to the LSST? Is it
no, unfortunately, with close to LSST, no, it's not there anymore because we had no money to rent the place for the prototype, from what I remember, and we were focused only on the full setup in Spain. Yeah.
Okay, and I really like the idea of playing with the dust. So could you comment on something that Božena already alluded to? How is this connection with the attenuation in the era of LSST going to be helpful to explain in terms of the main sequence diagram, which is, as you mentioned, it's no more as a main, but more like a convoluted main sequences, so to say.
So what we found with the last paper, and also what we are working now with a group from Chile as well, that we can somehow use the stellar mass, like the roughly calculated stellar mass, as a prior for one more for additional calculation for attenuation. So we have some priors. We have to have some priors, and for normal galaxies, we can say that we have some relation, but it's not really the relation yet, between stellar mass and attenuation in far UV band. So you want to use this as a prior for those SED fitting tool as SIGAL, and it looks that it works somehow, but still we have to obtain the stellar mass first, and it's some kind of a circle. But yes, it's something we are doing now because we found it as a huge problem for this amazing LSST instrument, for which we are going to have only optical data, mostly optical data. Yes. So, but maybe we can connect the far UV attenuation plus the roughly estimated stellar mass.
One more question, or we really deserve the coffee. So this is the end of the astrophysics session. So let's thank the speakers again. And coffee is waiting downstairs.
Welcome everybody to the second session of today, and this is the last session of this conference, gravitational session, and the first speaker is Piotr Chruściel from the University of Vienna, who used to work here at CFT, right, and did his PhD under supervision of Professor Jerzy Kijowski.
I never worked at CFT, but I was a PhD student.
Okay. Okay, so the floor is yours.
Thank you. Yes, good morning, everyone. Thank you very much for this invitation. I'm pleased to have been the first PhD graduate of CFT in gravitation and one of the first 5 in all fields, apparently maybe the 3rd even, but so I maybe not quite on the podium, but not that far. So I was extremely impressed by the results that we have seen here, and so I think it's quite a good set of achievement for a 40 years old. So that's a nice scientific career. What I wanted to present you is an experiment which I'm involved in at the University of Vienna. This is about gravitating waveguides. This is done within a collaboration within something called the Vienna University Research Platform TURIS, and TURIS stands for Testing Quantum Gravity Interface. The research platform means that when we want to do something, we don't need to ask the dean. So the dean is happy because he has less work, and we are happy we don't have to ask him. The colleagues involved is the Philipp Walter, who is an expert in entangled photons, Markus Arndt, who is producing amazing matter waves, Aspelmayer making nanomechanical devices. I'm contributing the theory part of this project. Bruckner is looking at what happens with causality when quantum physics is involved, and we also have a colleague from Alves from the Faculty of Astronomy. And the question we are interested in is that how does gravity interact with quantum systems? And more precisely, how does a photon feel time, whatever this means, but then how do entangled photons feel time? So there's been a lot of experiments about testing gravitation in various domains, regimes. So of course, classical physics, Newtonian gravity is something which is I don't have to talk about. We've had a lot of tests of classical physics and general relativity, and there also have been tests about Newtonian mechanics, Newtonian gravity and quantum mechanics. One of the things which is really missing is to have something which shows how general relativity interacts with quantum mechanics. So what we claim is that none of the experiments that have been carried out today show both signatures of general relativity and quantum mechanics, and this being specific to these two fields. And our hope is that we'll be able to do something, contribute to this topic with photonic quantum systems. In order to convince you that there were no tests of general relativity and quantum mechanics, let me review some of the tests which are known. There are 4 classical tests. I'm going to talk only about 2 of them because the first 2 ones, and I let you try to remember from your undergraduate physics which this might be. There's 2 classical tests which don't have anything to do with light, and so I'm going to review the 3rd and 4th classical test, which has to do with light. So the first being gravitational redshift. The gravitational redshift is something that been derived, proposed or postulated by Einstein already in 1907, well before general relativity, just based on equivalence principle. And in 24, it has been given some experimental evidence by, well, actually in 25. So Eddington pointed out that you could test the gravitational redshift using neutron stars. First tests were done in 25, and there was a series of them, and the latest one by Hubble, which measure the gravitational redshift in a strong gravitational field on a neutron star, Sirius B, to quite a good accuracy. Well, the gravitational redshift has several flavors. Of course, one of the best known ones is the Pound-Repka experiment, where you're sending photons from I always thought they were sending them down, so from the top floor down. Apparently, in this cartoon, they're sending them from the bottom of this building at the Harvard University campus up, and so that was an experimental test on Earth of the gravitation redshift compatible with general relativity on a height of 22 meters. You get a redshift that you can measure by using the Mössbauer effect. That's been improved. Well, there's an interesting experiment 72, which usually is taught in courses as being a confirmation of special relativity, but it's actually a mixture of both, of special relativity and general relativity. So what you do, you send a clock on in an aircraft, and because the aircraft is moving, there's a time dilation coming from special relativity, but also because the aircraft is not rolling on Earth but flying, you have a gravitational redshift effect, and it turns out that for this kind of numbers that you get for a flying aircraft and at the height they're flying, the effects are comparable. So if you send one with the rotation of the Earth or against the rotation of the Earth, you're going to get two different results. If you cancel them out, you're going to get the gravitational redshift effect, right? So this was confirmation at 10% accuracy. Now, a much more accurate experiment involved rockets or a balloon experiment by Vessel and friends in 79, where they could confirm by sending a balloon and making same kind of thing. So now, not anymore special relativity, but just the gravitational redshift to an accuracy of about 1 in part in 10 to the 4th. Here is an example of the success of a failure. This is there were two satellites from the European GPS network launched in 2014 in Dorisa and Milina. And normally these GPS satellites are supposed to be on geocircular orbits. But, well, this was Soyuz equipment, something went wrong, and they ended up being relatively eccentric orbits. And so I'm not sure how good they were for GPS, but they were certainly excellent for testing general relativity. And so here you see the redshift of the signal calculated from, fitted from general relativity, and the points here are the measurement points as the satellite orbits along its eccentric orbit. And if you can see that the residuals here are less than 1 nanosecond, in fact around 1/10 of a nanosecond, while the effect is order of 200 nanoseconds. So this is one of the best tests of gravitational redshift so far. Good, so this was number 3, still gravitational redshift. Now in a, well, an experiment having something to do with quantum, because it was using, well, I mean, in some sense, these clocks are very precise clocks. They're using quantum effects, but they're using quantum atoms. They're not using quantum light. Here is another one of these experiments. So what is remarkable about this experiment, that this is not anymore satellites, or which is 10,000s of kilometers, or maybe 20 meters in the in this Pound-Repko experiment, but with a very poor accuracy. Here it's just moving 1 meter 2 clocks, and well, their claim is that they can see the gravitational redshift. When I look at this figure, I'm not sure that they see something, but I mean, you can very well. Okay. Okay. Well, with atomic fountains, right? So I'm going to come to that. But so, well, I mean, if you're convinced that there is a clear effect here, then good. I'm not. But some such claims were done, and right. And so let me make it clear. All these experiments had to do with classical light in interacting maybe with quantum clocks, but there's nothing of general relativity interacting with a quantum system at this level, and that's I want to convey this idea, and I hope I'm making it clear, so, step by step. Good. So what is the fourth step? The fourth test. So this is not unrelated because it's about propagation of light in a gravitational field, but it's well, it's slightly different because here you're really looking at accumulated time difference when things are moving between 2 points rather than phase shift. They are related, but this is viewed as a different effect often in the community. So the Shapiro effect was the following. Well, you're just sitting on Earth here, sending a radar signal to, well, to, I think, is it Venus? Or I think it is Venus, right? Does it say here? Anyway, so to another planet. And this radar signal is coming back. And you calculate how time it takes to go back and forth. So you can calculate how time it would be if the space-time was flat. And you can calculate how much time it takes if the space-time is a Schwarzschild metric. And in a Schwarzschild metric, the light takes more time. So more or less? Well, it's a pure delay, right? So it's coming back later, right? Yeah, it is coming back later, and so so you can measure this and compare with general relativity. Well, this experiment has problems because, of course, the effect is largest when you're coming near to the sun, but the sun has a corona and light propagates differently in a corona than in vacuum. So there have been various objections to how accurate this thing was, and of course Shapiro did take this into account. There are much newer versions now where we're sending signals to the Cassini probe, in which case you don't have this problem coming very near to the sun. It's very far away. It's a weaker field, but the thing accumulates. So you can get accuracy of 1 part in 10 to minus 5 by measuring this Shapiro delay. Okay, so this was all classical physics, and there are experiments which make gravitation interact with quantum mechanics. And the first thing was the Colella, Overhauser, and Werner experiment from '75, called as Cow experiment. So where you are actually interfering neutron beams. So you're sending a beam of neutron. You split them on some kind of material and recombine them again. And so all this is an apparatus which on a table which can rotate. So when you send the signal at one, you change the position of the apparatus, the height of one beam is moving higher than the one below. Therefore, it's moving in a gravitational potential, which is different. So you take your Schrödinger equation that we've all seen in the quantum mechanics 101 and put a Newtonian potential. Well, this is the same as a Maxwell potential, so there isn't much to do. You can just calculate the difference, and you get exactly what you expect. Right? So you get a phase shift coming from the interaction of the wave function of a neutron with the Newtonian gravitational field. Of course, it is a test of general relativity in the sense that Newtonian physics is a limit of general relativity, but you don't need any general relativity to do this. You do quantum mechanics and Newtonian gravity, and that explains this. Well, meanwhile, there have been various fancier or related experiments where neutrons. So one, a nice one was when you're sending a beam of neutrons between two plates. So the plates act as infinite potential barriers. So you have an infinite potential here, linearly changing gravitational potential in this direction, and another infinite barrier. So again, an exercise in Quantum Mechanics 101. You just solve the for eigenfunctions of the Schrödinger equation in one dimension with a linear potential. You get something called Airy functions, and with the beam of neutrons, you can actually measure Airy functions directly. So they get a perfect experiment with this. Again, quantum mechanics with Newtonian gravity. And so the experiment that Dążewski mentioned, this is the atomic fountains. So what you do here is that you have a cloud of atoms that you manipulate here using laser beams. And the manipulation consists of cooling them to as much as you can so that they are as cold as you can, and then you kick them up with a laser beam so that they go up. You kick them up with another laser beam so that they go down. So you can think of this as really, and you look what happens when things interfere when they come back. So you can really think of this as an interferometer where some of the atoms remain here in the lower arm of the interferometers. The beam splitter is this first laser beam which kicks part of the atoms up. The mirror is another laser which kicks the atoms down. And so this is this picture here, right? So you have a wave coming, being split into two, and without gravity, that would be the classical trajectory. With gravity, well, this trajectories are bent, but you're not doing classical calculations. You just take your Schrödinger equation, as I said, and you make and you see how the interference pattern is depends upon moving the changing the height of the mirror, or in other words, where the reflecting laser beam kicks the atoms down. Good. So. Well, this experiment is very impressive, gets extremely good accuracy, measures the gravitational constant G to in a completely different regime that we are used to. I mean, so G is known at the level of planets, G is known at the level of things moving on the surface of the Earth, but it's never been measured on a such scale acting on quantum systems. So, but there was a lot of discussion in the literature whether this is measuring proper time of photons, general relativity, or is it quantum gravity. But here, there's I mean, the objects that interact here, well, light is involved only in steering the system. All the effects are taking place on massive objects. So, and everything that has been done here can be explained by the Schrödinger equation with a Newtonian potential. One point being that there is no Newtonian model when photons are used, because photons are supposed to be massless, and there's no classical gravity theory for massless objects. So the experiment we propose to do is to make a quantum test of the Shapiro effect, or maybe a quantum test of the quantum gravitational redshift, or maybe equivalence principle with photons. For me, these are various names which are kind of sound bites describing an effect which the bottom line, you really need to take Maxwell equations in a curved gravitational field, well, in this case, a weak gravitational field, and calculate them and see what happens. Now, whether this is a Shapiro effect, well, Shapiro effect has only to do with the delay of arrival times. No, it's more, because you need to solve Maxwell equations. It's not only calculating a time delay. And gravitational redshift, again, it's more. You really need other things. So, in some sense, these are tests of this, but it's more. It's really a test of whether quantum mechanics in a curved space-time gives the correct predictions for this kind of experiments. So what's the point here? Well, we have a laser, we're sending a wave, and now we measure the arrival times here, and now we're moving the either the laser or the light beam, and then we're measuring again the arrival time, and so this difference is what we want to check. And we want to do this not with classical light, but with photons or with entangled pairs of photons, and with a height difference of about 2 meters, right? So you want to do this in a lab. So the experiment has been, the proposal goes back to some 4 years ago. You can calculate the phase shift expected in this experiment on photons described as wave packets coming in your wave splitter. So the height is 1 meter, and now we have 100 kilometers here, and now 100 kilometers to achieve is not, well, in vacuum seems to be problematic. You can have 100 kilometers in LIGO, because in LIGO the arms are 3 kilometers long, but it's a Fabry-Perot cavity, so the light goes back and forth several times. But then it's hard to move LIGO 1 meter up in a stable way. So the trick is just to put a waveguide here, right? So rather than having light propagate in vacuum, we put a waveguide and we propagate. So we have 100 kilometers length path of light because it's in a waveguide. So with 1 meter here and 100 kilometers in each of the arms, we can get one gets a phase shift of 10 to minus 4 radian, which isn't much, but which is apparently bread and butter almost for my colleagues in Vienna. So it's not really bread and butter, but they claim they can achieve this with enough fine-tuning of the machines. So one needs to worry about photon losses. That's one problem. One needs to worry. Yeah, so there's this frequency change of 10 minus 17 corresponds to 10 minus 5 radians. So you need to scale it maybe by a few factors to get something which you can measure. This corresponds, by the way, to something which is called strain in the gravitational physics community. So how the change of distance by unit distance, that's how the metric, that's what the metric does to you. A metric tells you directly how the distances change. And so this corresponds to a strain of 10 minus 16. If you think about LIGO, which is 10 to minus 23, then of course we are it's a ridiculously big effect compared to LIGO, but of course the machines are well, you're working in a completely different machine regime, right? So there are many challenges for this experiment. Well, fiber thermal noise, systematic errors, Seismic noise. Well, seismic noise is probably the easiest one to get rid of because we have the experience of the LIGO people, how to get rid of the seismic noise. So this is so you have to move everything, put everything in a on one of these suspension devices from LIGO. Then, well, if thermal noise, well, you need to work in an isolated system. Acoustic noise, laser noise, well, this is quantum effects, which then are from a different world. Let's see, now the worst thing, the biggest problems are probably all these nonlinear effects, which are especially annoying if you wanted to use this kind of devices to something else, like maybe detect gravitational waves. Right? So detecting gravitational waves on your desktop in a machine which has 2 meters height and fits on this table would be quite a nice thing to do. And so these waveguides seem to be completely useless for this purpose because of this thing. Somehow, if you want to gain sensitivity, well, of course, now we're not talking about single photons, as this experiment is supposed to. That's the main aim at this stage. But to detect gravitational waves, you'll probably be using classical light there, and you need a lot of classical lights to increase the sensitivity. And the problem is that if you put too much light in a waveguide, it's going to melt. So that's a serious concern. And there's been a lot of progress with waveguides in the recent years, and maybe in 10 years they'll be good enough so that one could actually imagine thinking about detecting gravitational waves with such machines. But today is actually completely out of question. So so this is a collaboration with Nergis Mavalvara from MIT, who is supposed to be, well, he will help us with the seismic problems. And I think my time is out, so is it? Okay, good. So this is well, we need money for this, so this is work in progress. So we're certainly working on constructing this. Doing the final machine would need a few million euros, so we're not there yet, but that's the plan. Thank you.
Thank you. Are there any questions, please? Professor Rzężewski?
You've mentioned entangled photon pairs. Could you elaborate a little bit? Would you send one guy up and the other down, or what?
Yes. So so that's the idea, right? So you send a noon state in the machine, and well, you're sending it in the machine. You don't know where it is, right? So it's in both arms, and
so either two go down or two go up. Yeah?
They both go down and up, and then you and then you measure. You use the home story to measure the effect, and so this has been done by Walter years ago, not measuring the gravitational field, but measuring the phase shift that you introduce by some other methods, right? So here the idea would be that the phase shift that you're producing with in this machine will come from the gravitational field, where you're moving the arms either by rotating the machine or by mechanically moving them, or maybe by electronically splitting the beam. Yeah.
But then the single atom at the beam splitter will do also the same thing, would go in both arms simultaneously. Where is the advantage of having a pair?
Here. If you have one, you'll get this response. You get two, you get this response. You get three, you get. Well, first you're checking that if you have a single photon, it's essentially the same as classical light. If you have two photons, a pair of entangled photons, the effect is amplified. So you get a response at the output, which depends upon the number of photons, which classically you don't. Right? So that's the part quantum field theory in a curved spacetime here.
You have been stressing this difference between classical and quantum, but electromagnetic waves are always made of photons. So when you have an electromagnetic wave, it is really testing the gravitational effect for photons.
Right. So I think the difference is at exactly at this level here, right? That if you send a wave or one single photon, you'll get the same effect just because the calculations coming from classical Maxwell equations in a gravitational field give you the same effect that quantized photons in this machine. But if you have two, then you had this factor here, which classical theory doesn't give you at all. And that is, well, in some cases, certainly been confirmed. So.
And the last question.
So I have a simple question. I suspect that the success of this type of measurement depends very much on whether you can make your waveguides identical or at least similar, because each of the waveguides can in principle add some kind of phase difference, and you have to make sure that these phase difference is the same.
This is a long story called stabilization, right? So you're absolutely right, that's a big problem. And of course they can't be identical, but what you can do is that you can make sure that they're as comparable as possible by using specific tricks from quantum photonics to be able to measure changes, right? And so that's called stabilization, and that's a long story.
I know time is short, so I'll just restrict this to a comment. In general relativity, the gravitational field is the curvature tensor. In all of the experiments you're talking about, with the exception of the Shapiro effect, that does not appear. If the gravitational field were different by an order of magnitude or 3 orders of magnitude, it wouldn't affect any of your conclusions. So you shouldn't say these are tests of gravity, they're just tests of acceleration.
Right, so that's certainly one way of interpreting this. That's what I said here, that's a test of, at the beginning, some people view this as a test of the equivalence principle at a quantum level. Fine with me, you can view that. Of course, the effect coming from curvature here would be a 7 order higher than the ones that we're discussing. So of course the VESO satellite, or Galileo satellite experiments go beyond, in principle, go beyond the linearized theory and therefore go beyond the acceleration. But this is a. But again, one has to be careful because, of course, again, curvature effects are much smaller than just the effect of the G00 in the metric. So one has to be. Yeah.
Okay, thank you. Let's thank the speaker again. And the next speaker is Professor Jerzy Kijowski, who is working at the CFT from the very beginning.
I decided to give a chalk talk, but for the chalk talk you need a blackboard, and the just recently the company which was responsible for providing us the blackboard has informed us that they will but with few days of delay. Therefore, I will squeeze a little bit my talk. The idea is to tell you something about relativistic research in general relativity. I will begin with reminding you that 120 years ago, in April of the year 1900, Sir William Thomson, Lord Kelvin, gave his famous speech when he mentioned two clouds hanging above the otherwise very clean horizon. And of course, everybody of you knows the rest of the story. And I have a strong feeling that during this 120 years, we are constantly fighting against those two clouds. And why two and not, for instance, three of them? Because if we put on one real axis different orders of magnitude, so here are things which are medium size, here is great, here is small, then we understand relatively well what is medium, and those two clouds corresponds to the boundary of this one-dimensional interval, and due to the topology of real line, the boundary is composed of 2 points, and this is why we have those two clouds. Of course, the boundary between what is medium, what is great, what is big, what is very big, shifts, and shifted also in this direction and in that direction. This begins to the technology, but still, what is we are not understanding neither what is very big and neither what is very small. Today I am going to tell you, I am going to talk about this cloud, which is related with relativity. However, during my 41 years spent at our institute, I probably spent even slightly more time working on that cloud. And for instance, Szymon Harzyński, who is chairman now, did his PhD, which had nothing to do with general relativity, but rather with quantum field theory, an attempt to formulate quantum field theory in terms of gauge invariance. However, today I am going to talk about relativistic research, and the general relativity is very often presented in different ways. However, the only physics in general relativity is that geometry is not given a priori, but is a dynamical object. Once you accept this, you immediately end up with Einstein equations, and this is a mathematical theorem. Apparently, this statement is false. For instance, Andrei Sakharov in mid-60s proposed to consider theory which is based on the Lagrangian. As you know, the Hilbert's Lagrangian is just a scalar curvature of space-time. So he proposed to add r square with some tiny parameter alpha, and he expected that such a theory will behave better for quantum field theoretical purposes. However, it turns out a priori this contradicts my claim that it is equivalent to the standard general relativity, because if you derive field equations from such a Lagrangian, you obtain fourth order partial differential equations for the metric. But we already teach our students at the first year that if you have 10th order equation, it is equivalent to the system of first order equations. You simply call 9th order derivative variable, call it x, 8th order y, and one of the equations is y dot equal y. And this is a trivial observation, and the same happens here. So this fourth order system of equations is equivalent to the second order of equations for different quantities, and more precisely, we have been observed that such a theory is equivalent to the standard Einstein theory together with some scalar field. Now, what about the origin of Einstein equations? So this observation that higher order equations are equivalent to lower order equations for a bit bigger system of unknown functions is trivial. However, if you what is also important, that those equations should not depend upon parametrization, or in mathematical language should be invariant with respect to the diffeomorphism group. Once you insist on that, then the lowest order term which you may form out of the metric is just precisely R, and this is just a trivial observation. Once I have realized that this was published already when I was working at our institute around 1987. Nowadays, those beautiful observation of the sky, this boundary from the solar system was shifted by many orders of magnitude, and we know much better, and the astrophysicists and cosmologists push us towards looking for dark matter. Okay, many authors just add different terms to this R and consider those theories. Now, all these theories are equivalent in the sense which I mentioned before to the standard Einsteinian general relativity with different matters. So one way to look for dark matter, for the description of dark matter, is to try to add just different matter terms. But the other one is to try to understand well the very nature of geometry, and this way maybe I will squeeze out this matter as a part of some bigger structure, which I believe is more relevant. However, the two methods are mathematically perfectly equivalent. So this was one. Of course, this theorem, at that time it was theorem about this precise model, but later on we were able to prove it for different type of Lagrangians. Recently, there is a general theorem that even if the theory is of very high order, which means that contains not only curvature tensor, but also its covariant derivatives up to a certain finite degree. Again, such a theory is equivalent to the standard general relativity together with appropriate matter fields. Let me finish this. And the second important direction of our research was gravitational energy. In general relativity, there are many fictitious waves, and for instance, observing them, Albert Einstein published a paper in 1937 when he proved that gravitational waves do not exist. Okay, so how to discriminate between those fictitious waves and those who really carry some energy? So for that purpose, the notion of the gravitational energy is very important. At the very beginning, people tried to mimic the Noether theorem, which we know from special relativity and so on. But if you think a little bit, you know that such an approach is cannot be satisfactory. Why? Because gravitational energy cannot be additive. If you take a volume and divide it by 2, for instance, V1, V2, then the energy contained in V is just the sum, V1 plus V2. The energy contained in the sum cannot be equal to the sum of energies contained in both. Why? Because energy, as we know, is equal to mass. Of course, the journalist version of this theorem, namely mc squared, is much better known, but I am working in geometric units, therefore energy is just mass. So, such equality would be inconsistent with the very notion of of gravity, because if I have mass here and mass here, they interact. Therefore, the interaction has to be taken into account. Therefore, any kind of energy density or pseudo density, people were inventing different things, cannot be cannot be there. We cannot obtain the energy just by integrating, because integration means adding contributions from different points. And in general relativity, different points are just different. You cannot add contribution from different points, and that's all. People were, of course, the notion of energy, of the global energy, was very well established already. So the so-called energy at space infinity was well defined in the famous paper by Arnowit, Deser, and Misner in 1956, I believe, or 57, and from that time the total energy in an asymptotically flat case is well defined, and I believe this is the last word which can be said. However, later on, because for purposes of gravitational waves, this is not spatial infinity, but rather a light infinity, which is relevant. For, in this case, Andrzej Trautmann, in his papers from 58 till 62, had an extremely nice way to measure how much energy is carried by gravitational wave. And this is really a way to discriminate between those fictitious waves, which do not carry any energy, and the true gravitational waves, which really carry some energy. Okay, but this was again an infinity, energy at infinity, time-like infinity. But what about finite energy? Because what we know about infinity? Infinity is far away, and Einstein, and from this point of view, I like very much this approach. Physics should be local, because infinities are far away from us, and any statement about infinity are suspicious. So what about the local energy? Of course, due to this fundamental observation, it cannot be local in the sense that we just gather contribution from different points, but Roger Penrose introduced a nice terminology, which I like very much, quasi-local. The energy, gravitational energy, should be quasi-local. Therefore, this means that it is not assigned to three-dimensional volume, but rather to its boundary. Therefore, the boundaries do not sum up, of course, and this is why this inequality can be satisfied. My idea, after Penrose papers, there was a festival of definitions. Nowadays there is more than 20, almost 30 different definitions of the quasi-local energy. Most of them are just ad hoc inventions. People were tended to find some nice geometric quantity which can be defined via a two-dimensional integral, and this is mine. The most proliferant is probably Yao, who and very good Chinese, previously American Chinese, nowadays more Chinese. He became, due to the polityka historyczna, historic policy which was imposed by the Chinese government. He became a Chinese patriot, and he produced, as far as I remember, at least 4 or 5 different definitions. Okay, in 1995, 97, I have published a bunch of paper where I observed that this definition has to be based on an appropriate choice of boundary conditions for Einstein equations. This point of view was not very popular. However, 2 years ago, one of those gentlemen, namely Stan Deser, published a paper when he admits the same point of view. However, the terminology he uses, I hate it, although the content is exactly the same. He says that the diffeomorphism invariance should be broken by imposing boundary conditions. Nothing is broken. I very much prefer the following terminology. The physical field contained in a bounded region is not a closed system because it interacts with the exterior. And energy, that is a Hamiltonian, is a notion which is well defined for closed physical systems. Therefore, you have to insulate your system from the rest of the world. And to insulate, this simply means not, that you do not break any symmetry, because the theory is always invariant with respect to this symmetry, but you take into account only a space of initial values, those which somehow is okay. The mathematics, how do you realize this idea in a mathematical way? This is a longer story which I am not going to mention here. However, in principle, there is a unique way to adiabatically insulate the interior from the exterior. At that time, I had an idea that because this is not yet decided, which kind of boundary conditions you have to impose. For instance, for a scalar field, you know that you have Dirichlet boundary condition, Neumann boundary conditions, and so on. And only Dirichlet leads to... when I have a discussion with those people who are proposing new definition of the energy, my answer is always like that. I will admit that your definition is perfect if you are able, when you apply your method to electrodynamics, you obtain E squared plus B squared half If you are able to do that, then I agree. But nobody till now was able. I had the idea how to do it at that time, but and the idea was that we should confront the nonlinear theory with the linear theory. The energy in linear gravity is much less difficult, and also recently there are few papers published in our group where this the energy of linear gravity has been practically fully analyzed. So the idea was that we should somehow that the correct definition must fulfill the following test. When you take expansion of full gravity with respect to the field strength, in linear approximation, it should correspond to the energy of linear theory. And however, I was unable to perform those calculations because they were very difficult. 20 years ago, I asked Jacek Jezierski to do this calculation, and under very simplifying assumptions, he was able to prove that what is called Hawking energy really fulfills this test. By the way, for the total energy, this test is fulfilled, and this is the so-called Brill-Deser theorem, and it was proved already many, I believe 30 years ago. But the local test had never been done. Partially it was done by Jacek Jezierski 20 years ago, and only last year and this year, a student of our PhD student, Piotr Waluk, finally was able to prove the theorem that in the linear approximation, that only the Hawking mass or Hawking energy agrees with what we know for sure in linear gravity, agrees with that. This, I believe, is a very important result, and I am very proud of that. Okay, I will stop there. I believe that the two most important trends in what we were doing were already reported. Thank you very much.
Are there any questions?
So let me only say that, of course, I didn't mention what Mikołaj is doing here. He is a younger generation which replaces us at the center. He brought new problems, but he is going to tell about his research now. Okay, thank you very much.
Sorry, can I ask a question?
There's a question.
Yes. So about the first part of your talk, about this equivalence between higher curvature terms and adding, having usual gravity but with matter fields. And I like it a lot because it's a chance to simplify the dictionary of all these models we're trying to test in cosmology. But there are also other ways we would like to test it. For example, there is this Etherington duality relation which connects angular diameter distance, luminosity distance, and redshift. And if if this relation is broken, then some people claim that we would add or we would observe effects of non-metricity. So my question is, can we extend this equivalence to curvature where torsion or non-metricity is present?
Okay, I have the following tendency that because torsion is a completely different object than connection. Because the gravitational field is described by the connection. This is related with the Newton's first law. Yeah, Newton's first law says that there exists an inertial frame. So gravity may be also formulated like this. At each point separately, there exists a local inertial frame, and that's all. This is gravity. Okay, but gravity is a much more general object, and of course connection may be symmetric or not, but non-symmetric connection is not an irreducible object. Non-symmetric connection is just always a sum of two things, completely different things, namely a symmetric connection and a tensor, which we call torsion. Okay, I have nothing against torsion. However, if I see the tensor field, I have always a tendency to call it matter field. And of course, mathematically, whether you call it like that or you insist in keeping this pair symmetric torsion plus symmetric connection plus torsion doesn't matter. Okay, so in this sense, it covers perfectly also the torsion case.
Thank you.
Okay, one final question.
Well, it would be rather a short comment. As we heard already, teaching was a very important component of the center mission from the very beginning, and teaching at university level, although of course we are not university but just the Institute of Polish Academy of Science. And nowadays lectures given by professors of the center can be viewed or listened to or found on our YouTube channel. And with that respect, I want to recommend a series of lectures by Professor Kijowski. First on special relativity, then on general relativity, and very recently on differential geometry.
Thank you very much.
Okay, thank you. So the next speaker will be Mikołaj Korzyński, who was already nicely introduced by Professor Kijowski.
Can you hear me? Yeah, I guess it works. So thank you very much for the introduction. I will tell you about a particular rather recent result of my group, which I find rather interesting and which is, I think, also very, very beautiful from a mathematical point of view and may have astrophysical applications. The title is Weighing Spacetime Along the Line of Sight Using Times of Arrival of Electromagnetic Signals. It's based on two papers. One of them is already published in Physical Review D. The other one is a little bit older. And here's the idea. So assume that you have got a space-time. I don't assume anything about the space-time. It's just four-dimensional with a metric of appropriate signature. And we've got a null geodesic connecting a point E in the past with a point O in the future. So if you emit a photon from this point of view, it will flow from this point, it will reach the point O, the observation point. Now, I consider two very small neighborhoods of the points, events E and O in this spacetime, and I assume they are sufficiently small that you can consider them effectively flat, although the spacetime here is not flat. In the first region, I assume I've got a number of clocks which are co-moving and which have been synchronized. This is basically a flat spacetime, so they just fly with the same velocity, and I assume that they send signals at prescribed moments, electromagnetic signals, let's say, some kind of discontinuities in the electromagnetic field. These signals then travel around the space-time, also near this fiducial null geodesic, and they reach the region O. And here they are picked up by another set of clocks, which are also synchronized and co-moving. They have the same velocity, but positioned at different places. And each clock registers the time of arrival of each of these emissions. There doesn't have to be 3 clocks. In fact, you need a bit more than that. Now, what I claim is that, from this data, we are able to measure the curvature of the space-time along the line of sight. And in particular, we are able, with some assumptions, we are able to measure the amount of matter along the line of sight, or more precisely, an appropriate integral of the stress energy tensor along the line of sight. And since the stress energy tensor measures how much matter we have, we basically weigh the space-time this way. And interestingly, you can do this measurement without any assumptions regarding how these guys travel through the space-time, what is their momentary for velocities, and also the way these clocks are positioned is not all that important. You'll see later why. Okay. How does it work? Well, first imagine that these clocks are very close to these fiducial points O and E. But you are allowed to place them at any point within these regions. I'm suppressing the time dimension here. I'm just asking about the where you place your clock. Now, if you place your clock a little closer to the point E along this null geodesic, it's fairly obvious that the signal will be registered a little earlier, and vice versa. And the same applies also to the other side of the geodesic. This is what is known as the Romer delays. Basically, the closer you move towards the source, the earlier you get your signal. And note that in the linear level, only one component of the displacement matters, the one which is along the line of sight. There is no dependence on the transverse effects. And also note that the rate of change is a little bit different on one side and on the other. This is deliberate. This is because of the time transfer effects or the redshift blue shift effects between these 2 points. So the exact dependence on the displacements on both endpoints does not have to be the same, even in special relativity. Now, assume now that these 2 regions are a bit bigger. In that case, you have chances to register also the transverse delays. So not just the linear order in displacements of the position of the clocks, but also the quadratic effects. Typically, what happens is that if you move away from this fiducial line, you get a small delay on both endpoints. Note, however, that these delays do not have to be, again, the same on the 2 endpoints. Now, here's the important point. These quadratic terms in displacements consist of 2 parts. One of them is the finite distance effects. They happen even in flat space-time. But on top of that, you've got the imprint of the curvature tensor along the line of sight, which changes somehow changes a little bit these quadratic effects. And you can register that. Okay, now in order to proceed, I have to introduce a bit of theory. So the first thing I want to introduce is something I call the product manifold. And that's basically a formal product of the space-time by itself. So a set of pairs of points, both pick from the space-time. And I look at the pair of points O and E corresponding to the emission and observation of this fiducial single photon. This is an 8-dimensional manifold. The tangent vectors here correspond simply to pairs of vectors at the 2 points. A tangent vector x here consists of a vector field at the point E and another vector at the point O. In fact, you can write these vectors simply by stacking the components of both vectors in any coordinate system, and this will work. More formally, there is an isomorphism between the tangent space to this product space and the direct sum of the tangent spaces at 2 different points. Now, I also make this thing a metric space. I introduce a metric tensor, and it's given basically by this space-time tensor at these 2 points. I take the part of the vector x at the point O, the part of the vector y also at the point O, and I just multiply them with the metric tensor at the point O. I do the same with the E part, and I subtract these two things, and I get a metric which is which is well defined and of signature 4,4. So this is now a proper metric space. And now here comes the most important part of theoretical concept of this talk, the local surface of communication. It's basically the geometric locus of pairs of points which can be connected by null geodesic. So pairs of points such that when you send a signal from E, it will reach the other point O. Now, this is a complicated set, in fact. The nice thing about it is that it defines the shapes of all possible light cones. So if you fix a point here at M and you take a section of this set, you'll simply get a light cone at the center corresponding to this point M. And you can choose the point M freely, so this is something like the union of all possible light cones here. That makes this structure very interesting. However, unfortunately, it is not a proper submanifold of dimension 7. What it means is that we would like this could in principle, this is a 7-dimensional object in principle, and an object like that would be a proper submanifold if in the vicinity of each point it would look simply like a 7-dimensional surface. But this is not the case. Even in the flat space-time along the diagonal, you have singular points, so points which don't quite look like parts of an immersed submanifold. On top of that, in a curved spacetime, you have things like multiple imaging and formation of caustics, and this causes this surface to intersect itself in a complicated way. However, you can at least hope that when you keep away from any caustics, then locally, if you just confine yourself to a small neighborhood of these 2 points, you will get something like an immersed submanifold corresponding to the points in these both regions which are connected by null geodesics. So I assume that this is the case. In a small neighborhood of O and E, I will describe this local surface of communication by standard geometric objects, the normal one form, which defines the tangent space or approximates the surface as a flat surface, and the extrinsic curvature, which measures the deviation from flatness. Now, the normal one form is very easy to get here. You simply take the tangent vector to this fiducial null geodesic, you lower the indices at the 2 endpoints, and you stack them together, and you get the normal one form. The extrinsic curvature, on the other hand, is given by an appropriate relation relating involving the curvature tensor along the line of sight. I will later tell you what it looks like. Just keep in mind that these things are not defined absolutely. You can always rescale them. This is because there is no preferred scale, there's no preferred parametrization of a null geodesic. And because of that, you can rescale both of these quantities. This plays the role of a gauge symmetry here. The proof of what I'm saying proceeds via something called the Singh's world function formalism, but I will not show the details here. Okay, so how do you get the extrinsic curvature of this local surface of communication? Well, you have to look at the first order geodesic deviation equation along this null geodesic, find the parallel propagated tetrad here, and then in this parallel propagated tetrad you can try to find the resolvent of this equation. This is a second order linear ODE. You can find a resolvent, so something that takes you your initial data at O and gives you the initial data being the deviation and its derivative at O, and gives you the corresponding data at E. You do it by solving the resolvent equation, which looks like that. And note immediately that it looks very much like the equation for the time evolution operator in quantum mechanics. You have a lambda independent, lambda is the parameter along this geodesic, lambda independent part here, and on top of that you've got a lambda dependent correction. If you just added I over H here, you would get a proper, the equation will look exactly like the time evolution equation in quantum mechanics. And that's very good. It means you can use the standard perturbation theory techniques to solve this problem, treating this as a small perturbation. Okay, once you get this W, this resolvent or the bilocal geodesic operator as we call it, you then do a complicated nonlinear transform of each of the 4 submatrices of this guy, and what you get here is a symmetric tensor on the tangent space TOE to the product space. It's not obvious that this is going to be symmetric, but it is true. Okay, so we have a symmetric tensor. What now? Now we restrict this tensor to the tangent space, to the local surface of communication. We get a 7 by 7 matrix from an 8 by 8 matrix, and this restriction is exactly the extrinsic curvature of the local surface of communication. So in the end, from the curvature along the line of sight, we get this extrinsic curvature, or we discover how exactly this surface is bent. But what does it have to do with the times of arrival? Well, imagine you introduce two orthonormal tetrads at the two endpoints of your null geodesics. They can be whatever. The vectors UO and UE denote the four velocities of our clocks. We can now create locally flat coordinate systems around O and E using these tetrads, using so-called Riemann normal coordinates. Now we can identify points with tangent vectors here. But this also automatically gives you a coordinate system in the product space, which simply consists of the coordinates we have introduced here and then coordinates we introduced here. We add a simple gauge condition to fix the normalization of L. And now what we want to do is to express this local surface of communication as a graph. So we treat x0, the time coordinate at the O, as a dependent variable, and everything else we treat as an independent variable. Why do we want to do it? Because x0 is nothing else but the time of arrival of a signal emitted at time x4 by a clock positioned at x5, x6, x7, and registered by a clock which is positioned at x1, x2, and x3. So this is exactly a physically motivated quantity. What we do then is to find a Taylor expansion for this thing. It's given by the normal vector to the surface and the extrinsic curvature components Q. Okay, so now we have a direct relation between the positions of these two clocks, the emission time, and the curvature along the line of sight. But can we do something else with that? We can do something else. We can do the inverse problem. So assume that we sample the times of arrival over many pairs of points. Can we reconstruct L and U perpendicular from this data? It turns out to be fairly simple. So each measurement corresponds to the position of at the region E corresponding to our emission, and another point O corresponding to the act of observation. So we've got a number of pairs of points. We can write down the equations for each of these pair of points. The equations turn out to be linear with respect to the components of L and Q. So if we have sufficiently many of them and they're linear independent, we can just get the components of L and Q. And geometrically, this is nothing else but finding a unique quadric through a given set of points. So this quadric has to pass always through the point OE, because these points are connected by null geodesic. But we have a couple of others we have sampled, and then we are looking for the only quadric which passes through these points. Its properties are encoded in L and Q. And this is always possible, provided that we don't do the sampling in a very stupid way, for example, by picking up these points all along one direction. So we can determine the local shape of the local surface of communication just from the variations of times of arrival sampled between two regions. But what does it give us? Well, you can show that in a flat space-time, the extrinsic curvature of the local surface of communication is very simple. Basically, it vanishes in 5 out of 7 directions, so 5 out of 7 directions are degenerate, and then you have, in appropriate diagonalizing basis, you've got 2 non-vanishing entries, which are inverse proportional to the distance between the two regions. But in a curved space-time, you have only in general, you have only 2 degenerate directions. Everything else is, well, whatever. Great. This means that there is a substantial difference in shape between a local slice of the local surface of communication in a flat spacetime and in a curved one. We want to make use of that. So the curvature somehow changes the shape. And we would like to detect this imprint of curvature, small imprint of curvature on top of this data. One of the problems is that typically we don't have any control over the orthonormal tetrads we have used on both endpoints. So we will look for two-sided Lorentz invariants here. And our group already knew one Lorentz invariant of this kind. It's a quantity we call the distance slip. So imagine that you've got a bunch of null geodesics which are initially parallel near the point O, a so-called congruence, and we follow it backwards in time to the point E, and we take some kind of small cross-sectional area of this congruence. We follow it here, and because of some kind of lensing, typically the area around E would be a bit different. So we take mu, which measures how much this thing has effectively shrunk. A very curious property of this quantity is that it's completely independent of the states of motion of observers you use to calculate the area here. So whoever measures the area, cross-sectional area of a congruence gets always the same answer. This is a non-trivial statement. And this happens on both endpoints, so this quantity is independent of who does the measurements of the two endpoints. Secondly, this quantity always vanishes in a flat space-time. It's always equal to 0. And another interesting point, for short distances, it's given by an integral of the stress energy tensor. You can also define the same quantity, but starting from the point E into O. It works pretty much the same way, but with E and O reversed. Why we're interested in this quantity? Well, it turns out that we realized that it's possible to measure it with very precise astrometry. So in astrometry, there's a couple of notions of distance in general relativity. One of them is the angular diameter distance, which was already described before. So we are looking at a luminous body of a given size, and we compare its cross-sectional area with the stereographic angle we see on the sky. This is the formula, and the thing is that this quantity depends on the for a given observer and a given emitter, it depends on the curvature tensor along the line of sight and the forward velocity of the observer, although not on the forward velocity of the emitting body. You can also define the luminosity distance by measuring the observed flux and dividing it and relating it to the absolute luminosity of a body. This way you get a different measure of distance, which depends on the forward velocity of the observer and the emitter, and also on the curvature, but it turns out to be completely related to the angular diameter distance and the redshift via the Etherington's relation. But we are thinking about a different measure, the parallax distance. So you imagine that you observe your luminous body from slightly displaced points. You combine the images, you see that the images are not exactly at the same point. That's the parallax effect. In a flat space-time, the delta x, the apparent displacement, is inversely proportional to the displacement here. In a general space-time, this is a more general relation, but still, you can define an average parallax distance if you take the determinant of this pi. You get a different distance measure, which also depends on the forward velocity of the observer, but not on the forward velocity of the emitter, and depends on the curvature. Now here comes the nice fact. If you compare these two distance measures, so angular diameter squared over parallax squared and 1 minus that, or 1 minus luminosity distance squared divided by parallax squared times this redshift correction, you get exactly mu. So you cannot measure this quantity directly. It's not possible to send photons backwards in time, but there is an indirect way. If you have one single body and you measure the distance in two equivalent ways, the difference will measure the curvature effect along the line of sight. Strictly speaking, there's a sign correction which is possible here with strong lensing, but I won't mention that. So measuring the relative difference between distance measurements to a single object, you get a curvature effect. This is independent of the states of motion here. This correction vanishes in a flat spacetime, and for short distances, it's given by integral. So you can express mu and nu using the data we have measured. So Q and L, the components of the vectors we have determined. You can show that in practice these quantities don't depend on the pair of orthonormal tetrads you have fixed at O and E completely. even though these components have been written here in a particularly chosen frame, this value is independent. This is not a trivial statement. It takes some time to prove that, but it's true. Okay. We can expand these two quantities in the powers of curvature using perturbative approach, so treating curvature effects as small perturbations. And you can show that in the leading order, all that survives is the stress energy tensor, contracted with the tangent to the null geodesic times appropriate linear kernels. So what drops out is the Weil tensor, which encodes the gravitational waves or the tidal forces, and the lambda. The mu and nu are dimensionless and not very useful physically, but it turns out that you can turn them into something more interesting. If you have pressureless dust and very weak gravity, you can show that mu is just the integral of the mass density profile along the line of sight with this type of kernel. Nu is the same integral with a different type of kernel. And using that, if we know the distance between these 2 points, you can turn mu and nu into the average matter density along the line of sight and the position of the center of mass, so the first moment of this distribution profile along the line of sight. Okay, I should mention the measurement protocol. How do you exactly place the clocks? So here is a possible setup with 13 clocks arranged in a simple way. You just place them along 3 orthogonal axes on both endpoints of a single one, plus you put 6 additional more along the diagonals. And you can show that with this setup on both endpoints, if you send your signals at -L/c, L is the size of this setup, you can derive exact expressions which give you the components of L, the normal vector, and Q, the extrinsic curvature, and then you can plug them into the into the definitions of mu and nu to get the curvature effects. The curious thing is that because these quantities are Lorentz invariant, it means that it doesn't matter how exactly you align this setup of clocks. It can be aligned in whatever way you want, and its 4 velocity is also completely unimportant. So the measurement automatically cancels out all the effects of rotation and or boosting the clocks here. And this is curious because each individual measurement of time of arrival is, of course, very strongly sensitive to the angular position of both setups on both endpoints or on their 4 velocities. But somehow, miraculously, we distill something that doesn't depend on that. How large is the signal, assuming that you do a measurement of this kind? So I assume that the size of the clock ensemble is L, the distance is much larger between the 2 clocks D, and the curvature scale of the spacetime is R, much larger than that. You can define dimensionless variables, write down a dimensionless version of the formula for the time of arrival. You have basically the Römer delay effects which are of the order of 1. Then you've got the finite distance effects multiplied by L/D, so the ratio between the size of the ensemble and the distance. And the curvature effects, which are L/D times D/R squared, so even smaller than that. So imagine that we have 2 ensembles of clocks in a kind of constant matter density. How large is the effect of the curvature in this case? With a bit if you do your maths right, you can show something like that. So imagine you've got a cylinder of radius L connecting these 2 points and of size D. You take the whole mass enclosed in this cylinder of this matter density. You take its Schwarzschild radius, so you imagine you scoop it all together and make a small black hole, and you calculate 1/c, the crossing time of a single photon. And that's basically the typical time, additional time delay due to the curvature effects along the line of sight. So it's quite small. If the whole mass enclosed in this setup is of the order of Jupiter, this will be 10 nanoseconds. If it's a pulverized solar mass, it will be something like microseconds. So this is typically a very small effect. Okay, I think it's enough to go to a summary. So variations of the times of arrival of the second order between 2 distant regions of the constant of space-time contain curvature corrections on top of much larger finite distance effects. And it's good to realize that The deep underlying reason is an exact geometric relation between the extrinsic curvature of the local surface of communication and the space-time curvature along the line of sight. Because of that, it's possible to extract two scalars quantifying the curvature impact along the line of sight from an appropriate sample of times of arrivals. And then it's possible to obtain the first two moments of the mass distribution profile along the line of sight under certain assumptions. What you get is a very curious differential measurement in which the curvature effects are shielded from potentially much larger contributions from the tidal forces of massive bodies off the line of sight, misalignment effects or velocity differences. The effects are, however, usually very small. At the moment, I don't have exact applications for that, but I think this might have some serious implications in binary pulsar timing if you do it right. Maybe it's also possible to do some kind of direct curvature measurements using light propagation with the setup, but it seems that they will be quite difficult. Okay, thank you very much.
Are there any questions? Please.
I'm not sure how your methodology differs from what people doing strong lensing includes, because recently they include not only the modeling of the lens, but also all the effects along the line of sight. But of course in a very specific setup. So it's more, your approach is more general, right? They do the same, but in a very specific realization of the process, right?
I suspect so. Okay, I do it in a bit different way. I don't assume anything about the space-time. I suppose that people who do gravitational lensing already assume that this is, for example, a thin lens where you have a Newtonian potential, which you can treat as a very... So I suspect then I suspect that this must be done in a somewhat similar way, but I would have to look exactly at how people do it. Julius, on the other hand, has found something very curious. People working in seismology do very similar things in the sense that they also have a slightly similar relation for the times of arrival of shock waves within the Earth. And they use the Hamilton-Jacobi equation to derive very similar relations for the linear term and also the quadratic term. And they infer, for example, they try to infer, for example, the existence of faults or discontinuities in the material inside the Earth from these type of quadratic effects on both endpoints. So I wasn't aware of that when we were doing this, but somehow Julius managed to find that this type of methodology works here.
Is there any more? Is there any question?
Just a quick one. So pulsar timing, you've got to find a bunch of pulsars that are close together for your region E.
No.
And then is it enough to have just us going around the sun to...
Okay, well, the setup I was thinking about would be a binary pulsar. In that case, the pulsar sort of samples at least along one possible plane, and on the other hand, you also have the annual motion of the Earth, which samples in another plane. The problem is that you don't have the sampling in all possible directions, so you won't be able probably to do this type of measurement. But still, I suppose that you can find some kind of curvature corrections even with this reduced type of data. Although it will be mixed with the tidal effects along the line of sight. You won't be able to get rid of the tidal effects. So the funny thing about this...
You need more sources.
Yeah, you need a multiple system of pulsars probably with orbits in different directions to be able to do it. And I don't think that nature is that generous that it gives you something like that.
Okay.
Are there any more questions? If not, then thanks all the speakers of this session. And now, closing remarks.
Thank you, Szymon. So yes, our conference is going to the end. I would like to thank the entire organizing committee. It was very difficult to organize conference during pandemic. Actually, I should say that the whole organizing committee were discussing many difficult issues. There were many difficult decisions to be made. Like 2 weeks ago, it was even not sure if we'll be able to have this conference on site, because the number of COVID cases was increasing, and in the Institute of Physics it was decided to maintain all the restrictions after several discussions with Director Późniak, trying to find a way to fit our conference inside fully operating big institute. We decided that it would be better to move it if there is any way to do that. And finally we find this place quickly and reorganized everything in 2 weeks, starting from the welcome evening through poster session, coffee breaks and so on. And in many cases Piotr Chruściel was super helpful, identifying difficulties, solving these issues, taking responsibility. So I'm especially grateful to Piotr Chruściel, who is over there. Many people were involved, apart from organizing committee. We have also program committee. It wasn't easy to find appropriate speakers, as there are so many candidates, and the fields were so well. Activities of CFT are so diverse, but I hope we managed, and you find these talks interesting. So would like to thank the program committee, and then I'm so very glad that we have the company Wypożyczenia.com. I'm sorry for this, and especially to Paweł, because there were many issues to be solved also during the conference, the problems with projectors and organizing the whole hybrid conference. Then I would also like to thank to this, especially to Teresa Wasilewska from this hotel, because she was very helpful. As you see, the poster session and coffee breaks are in a bit crazy place. It's actually kindergarten, and they arranged this kindergarten so as we will have safe conditions to drink coffee. And I would like to thank to Justyna Cemrzyńska from the Aleksander Jabłoński Foundation. They are co-organizing this according to our agreement. They were responsible, for instance, for all conference materials and coordination of these tasks, especially at the beginning, but also for the book of abstracts and for the registrations. So with that, I hope that I express my thoughts about all these people's involved, and maybe I will give the mic to Adam, and then we'll have a conference photo finally in this place.
Exactly. So what I wanted to say is that Krzysztof didn't mention one person, which is actually the most important person in organizing this conference, so himself. Yeah. So I don't want to take much more of your time, because we have to eat lunch and take a photo. So I just hope that we will meet in 9 years to celebrate the more round anniversary, which is the 50th one. Thank you very much.
Okay, thank you. So now I propose that everyone will come over here, and we'll take the conference photo just inside this room, because we'll use these stairs. Że właśnie przy tym oświetleniu wyjdzie, ale to Paweł zrobisz nam... Tak. Bez maseczek. Nie wiem. Trzeba szybko stanąć. Musimy zdjęcie zrobić w mniej niż 15 minut i...
No czekaj Piotrze, ale zdjęcie.
Right everyone, can I have the people who are a bit shorter on the back, in the top of the stairs? People who are taller, please stand in the front.
But we have stairs here, so
Dać element doświadczenia. Widzę, że jestem doświadczony. Tak, każdy sam powinien. Średnia, możesz też.
I don't think this comes make one more line.
yeah, that's
Everyone smile, please. Look at me. Say cheese. Say science.